Ruth and Ilya Baldin. And they will update on Fabric. And then we have Eli Kafuri from USC, University of South Carolina, talking about hands-on labs on Fabric. Those are, Eli will present with more detail, but a library that is available on Fabric. We'll have a break and then 2 hands-on sessions on the fundamentals of P4. Day number 2 is going to be SciTNC, buffer sizing, congestion control by Doug Southworth, Indiana University, and then Neil Carwell will provide updates on PBR. And then we'll have 2 hands-on sessions where we will be using P4 for monitoring buffer queue and occupancy, and another application on P4, calculating packet inter-arrival times with P4 switches. So that's the workshop. Before we start, I want to make you aware that all the lab libraries that we build at USC, there are much more than what we're going to be doing here. If you are interested in using any of these, trying, please email the contact information that is here in this website, Jose Gomez. And feel free to visit this website where we have all this training material. With that, I will start. I don't know, Jason, if you want to say something else before we go to our third presentation.
No, I think that covers it. And certainly if people have questions during or after and you need to contact any of us, certainly do so. Epic is always here to help depending on what your needs are, if it be cyber infrastructure or security or any of those things.
Excellent. I think Paul Ruth will present this, and I will give a brief intro to Paul. Paul is an assistant director of the network research and infrastructure at RENCI, University of North Carolina, Chapel Hill. He has been a member of RENCI's network research and infrastructure group for over 10 years. During this time, he has contributed to several large computer networking and cloud testbeds, including Genie, Chameleon, and Fabric. He received a PhD in computer science from Purdue University in 2007. He currently leads the advanced networking efforts for Chameleon and is a member of the leadership team of Fabric. Paul, thank you for being here today. We appreciate very much, and I will let you. I don't know if Ilya is here too.
Yeah, I don't see him on the list. I see a bunch of other RENCI people in here, but I don't. Okay. There's a lot of people. Maybe I'm just not looking in the right spot.
let me just briefly recognize Ilya also. Ilya is the PI of this project called Fabric. He leads RENCI network research and infrastructure programs. He's a networking researcher with a wide range of interests, including high-speed optical network architectures, cross-layer interaction, novel signaling schemes, and network security. As I said, he's the PI for NSF mid-scale testbed called Fabric, which supports experiments with future internet technologies. Before coming to RENCI, Baldin was the principal scientist at the Center for Advanced Network Research at the Research Triangle Institute and a network research engineer at the Advanced Network Research Group at MCNC, where he was a team member and a leader of a number of federally funded research efforts. He holds a PhD and Master of Science degrees in computer science from NC State University. With that, Paul, I will let you share your screen and start the presentation.
Yep, I just need to find my screen. All right, do you see some slides? Right, that looks right.
Yes.
Okay. All right, so thank you, Jorge. Like was introduced, Paul Ruth from RENCI at UNC Chapel Hill. Been working on a lot of different NSF testbeds for a lot of years. And here today to talk about one of our newest ones that we're most excited about, Fabric. And it has a lot of ties to P4 and all the things that you're going to learn about today or over this workshop. So hopefully you'll learn some things about P4 and maybe use them on Fabric after this talk and after your experiences here. So the first thing is just Fabric. Like, what is it? I think probably a lot of people on this call have heard of Fabric, but we're going to I'll tell you more about it. So Fabric, first off, it's a NSF mid-scale research infrastructure. What that means is that it's part of the NSF mid-scale program. And it's basically an infrastructure that's somewhere between $20 and $70 million is what that means. So it's a pretty big scale, like very large scale, or not technically large scale, mid scale infrastructure, but for you it'll be like it's not small. So what it is a NSF mid scale research infrastructure that empowers researchers to securely prototype and validate disruptive network designs in an environment that closely emulates the real systems that computational science uses today. So you can kind of think of it as a scientific instrument or a laboratory that enables experimentation with new paradigms of distributed applications and internet protocols that and here's the most important part, is that they run both across the network as well as within the core of the network. And this is obviously very interesting to people that are studying programmable networks such as P4 and the reasons why you guys are here today. As was mentioned a little bit before, NSF or the Fabric was funded in 2019. It's currently, we're getting close to completing the construction phase of Fabric. We're in fact done with the construction phase in September, which is next month. So we're pretty close to the end of the first phase of our project. Following the construction phase, Fabric will enter its operational phase. And this operational phase will transition into focusing on onboarding lots of users and trying to get different experimenters to use Fabric to do interesting experiments, try to help them build their experiments, try to figure out what needs we overlooked. Maybe if you have a need for a specific experiment, we can still have time to incorporate it into Fabric. Despite the fact that we're not open, we've actually been partially open for the last couple of years. We have quite a few users already that have been kind of beta testers, but they've kind of outgrown the beta tester phase and they're doing actual research projects now. As was also mentioned before, our fearless leader is Ilya Baldin, who also works at RENCI at UNC Chapel Hill, but there's 5 core institutions that are building Fabric. These institutions are University of Kentucky, Clemson, RENCI at UNC Chapel Hill, University of Illinois, and ESNet with the Energy Sciences Network. And that's the core institutions, but we also we have locations and sites in all over the world, really. So we have a whole bunch of collaborating institutions and organizations that are helping support our infrastructure, as well as supporting the testing and evaluation by contributing users that are doing early experiments. So that's great too. A little bit of just a sense of scale for those of you who haven't quite seen it yet. This is a map of what Fabric will look like next month. We have a few sites that aren't quite deployed yet. But what it is, Fabric has a worldwide footprint with 33 locations interconnected by dedicated network capacity. With some of this dedicated network capacity is 100 gigabit per second, and that's the lines shown in blue here on this map. But other links we have are dedicated 1.2 terabit per second, and that's the links shown in yellow. And what these things are connecting is all these sites, these Fabric sites, as we call them. On this map, we have 33 sites. Each one of them is a small cloud computer. And this is a cloud where our users, our experimenters, can deploy private routers and switches alongside traditional compute and storage. And all of it's augmented with advanced accelerators, such as GPUs and FPGAs and different advanced programmable NICs. These user-controlled and network computational resources are connected with the network circuits, with dedicated network circuits between the sites, and these circuits are dedicated to the user. So when we use some compute resources at one of these sites and connect them, it's all dedicated to you for your experiment. You can think of Fabric kind of as a research cloud. So it's really like a cloud computer where you would typically get compute and storage, but we're providing access to the low-level programmable network resources in the core of the wide area network. So it's the cloud piece, but it's the core of the network, but acting kind of like a cloud. So notably, in this map, Fabric partners with Internet2 to offer its users the ability to directly connect experiments into public clouds using Internet2's Cloud Connect service. That's a pretty powerful feature. And beyond just the US, our original mid-scale grant was for 28 sites in the United States. They have since added the University of Hawaii site because that's a strategic place to have some networking resources. But we also applied for an NSF IRNC grant, which is the International Networking. I forget exactly what IRNC stands for, but we were given some extra money to build what we call Fabric Across Borders, or FAB for short. And what this has allowed us to do is to put 3 sites in Europe and 1 site in Tokyo. So we have sites at University of Tokyo, University of Bristol, University of Amsterdam, and at CERN right next to the particle collider, as well as access to dedicated circuits that go across both oceans, and then as well as dedicated circuits that go to South America, where we're trying to work with people at RNP in Brazil, as well as some other people in Chile that work with telescopes and things like that. So that's where our footprint comes from. In addition to like all the core sites, we have, you can see in the map, we're at a lot of major universities where we have a site at the university. If you want to site at your university and we can come up with the money, we'd like to put one at your university as well. So talk to us. There's, in addition to just the sites that we're connected to, the Fabric sites where we have our cloud compute, we also connect to things outside of Fabric. So we have this concept of a facility port. So this is a program. It offers the programmatic ability to extend experiments beyond the immediate footprint of Fabric. And a number of these facility ports are already operational, like the ones that connect the Chameleon testbed as well as the Cloud Lab testbed. We even have an experimental one at Rutgers that connects a cryo-EM microscope to the testbed. And a lot more of these facility ports are in the works, and we will eventually be able to add connections from Fabric to lots of different facilities and campuses and various other places. If you are interested in connecting something on your campus, in your laboratory, or some facility that you know about, let us know, because we are interested in growing the footprint of Fabric to connect to lots of other facilities. I've already pointed out that Fabric connects many of the facilities and services that we all use for scientific computing with user programmable networks. But this is sort of an evolution of what's already existed. A foundational tool of scientific computing is connecting a lot of these facilities that exist out in the world across dedicated networks. Today's scientific computing is really dependent on this. So like scientific computing is about connecting huge amounts of data and instruments that are spread out across the world, connecting with the internet and moving data back and forth between all of these facilities. A lot of times you use this for staging data and transferring it between compute facilities, or transferring it to and from big data repositories or big scientific instruments, as well as transferring data between big compute centers and maybe your campus or a cloud. And increasingly, these systems are being used in in ways that they weren't before. So a lot of them are you're pulling data or data streams directly from instruments, such as the Large Hadron Collider or these microscopes that are on different universities' campuses. At the same time, it's what we're noticing is that it's becoming really common for scientific users to integrate a whole lot of facilities into a single application, such as like an advanced computational workflow that involves several stages that ingest data, process data, and then disseminate the data to various other scientists that maybe have a workflow of their own. Sometimes these workflows even control remote instruments or even use sort of edge computing and like are widely distributed for federated learning at the edge in time inside a smart city or something like this. So we have all these systems that are connected with the network, but like things are evolving and they're getting more sophisticated. Much of what the scientific computing users can accomplish today is a result of these powerful resources and tools that have been developed over many decades. I mean, a lot of times these are like traditional tools, such as just large compute centers or advanced workload managers like Slurm and things like that. More modern resources and tools can be a response to specific community needs. Like for example, there's a tools like Globus that are used for big data transfers throughout the network, or there's lots of opportunities enabled by new underlying technologies like clouds, which have really transformed the way like loosely coupled and scientific computing is performed, or science DMZs, which I think you guys will talk about later. I saw that on the schedule, which greatly increased the speed and efficiency of transferring data between campuses and big data transfer nodes at big computing centers. And this was kind of a big innovation that helped a lot of the performance of scientific computing. And now we have Internet 2's AL2S system, which allows you to create dedicated circuits between campuses, as well as connect to their Cloud Connect system, which enables on-demand high bandwidth connections between campuses and the public clouds. So these are sort of new tools and that are adding to this infrastructure that has been built over the decades. So all of these tools are great, but the reality is that the reality of the internet is that routers are still only designed to store and forward packets. This is just a truth that hasn't changed for decades. When you design an application in these environments, you're limited to running that application at the edge of the internet, and any protocols that you want to optimize or do any tricky things you want to do have to be optimized from these edges, right? But a lot of, especially the NSF, our program managers are talking, they're putting a growing emphasis on something that is starting to be called the edge core cloud paradigm. And this is where applications run across multiple facilities and platforms. So this is one application or one distributed application that's running across the edge of the core and the cloud. And in this context, you have all these data centers and instruments and the clouds. They're kind of working together as one. Currently, end-to-end performance, if you're going to do this, is usually achieved through bigger pipes that are dedicated to you, often using Internet 2's AL2S system, or optimizing your data transfer nodes and science DMZs. But a growing footprint of distributed data and compute means we need to scale up and re-optimize these data transfer nodes and science DMZs across more distributed points within the network, because we now are getting to the point where we don't just know that these data is going to be transferred from campuses to data centers. We're doing things at the edge, and the edge means we're doing it absolutely everywhere, like in your phones and cars and everything, right? And so we need to be smarter in the core of the network. So another way to think about this is that there's a lot of processing capabilities in these instruments and data centers and clouds that we've been using for years, but we don't have this processing capabilities in the core of the network. And this is a limitation that's imposed on all of us right now. So there's this interesting quote that is probably not actually said by Henry Ford, but people attribute it to him, that says, so Fabric is a smart programmable cyber infrastructure. And the interesting quote from Henry Ford is, if he had asked people what they wanted, they would probably have said faster horses. And of course, he was trying to build cars for everybody, right? So he had a different answer than what people would probably want. And it turns out a lot of people like cars, and probably not too many people want to go back to using horses. And I think that's something similar is happening today, because if Henry was designing the internet and we saw routers that only forward packets, he probably would have asked, like, what do you want out of the internet? And people would have said faster networks. And I think we think that we're at an inflection point similar to the 90s when the internet was becoming popular and HTTP was coming on the scene. And HTTP made it's very interesting, very easy to share information and data via the web. But it would have been very, very difficult to predict all the uses of HTTP that we have today when you were in the 90s. So in the 90s, it was about the web and sharing data. But today we use it for all sorts of like REST interfaces and just absolutely everything, right? So it's hard to imagine this small little changes and how big of an effect it had in the future. So we think that smart programmable cyber infrastructure connecting all these scientific computing facilities and clouds and campuses and instruments is an opportunity to rethink the core of the network and how we use it and how we develop new layers of software to make it possible to deploy applications across the edge of the core in the cloud. And that's kind of where we think we are today. So towards this goal, Fabric is a testbed that allows us to run applications anywhere. You can run them in the edge, the cloud, or places where the routers and switchers are found today. This enables in-network processing, intelligent caching of data, distributed AI, and many other uses that are really difficult to predict at this time, but soon might be really commonplace. So Fabric scales both in geographic size, so we're all over the US for sure, but the world to some extent. So we scale even geographically, but we also scale in terms of performance. So we have really high bandwidth links, and we have modern accelerators that you can get in the core of the network. We mentioned that Fabric has 33 sites connected with 100 gig dedicated network, layer 1 network circuits. But we also connect or will connect to all the real facilities that you already use. If there's one that you want to connect to, we don't connect to it, let us know. We will do our best to try to connect to it. This includes like all the NSF clouds and test beds, different HPC centers via access, compute centers, and all the campus cyber infrastructure that we can get access to. If your campus or facility wants to connect to Fabric, or if your campus or facility wants to connect to Fabric or connects to Fabric, it'll also allow you to connect your facility to all the other things that connect to Fabric, and that's what we're aiming to that's the service we're aiming to provide. One thing to know is that Fabric is not intended to replace any of your existing infrastructure. It's really it's not going to replace AL2S or your Amazon AWS Direct Connect connection. Instead, it's meant to be a really powerful sandbox for experimentation that minimizes the security risks and disruptions to your production environment. I mean, it's really infrastructure as software, and it enables a rapid test cycles with automatic redesign. So what it's really doing is it's a sandbox for you to deploy things that would just not be safe to deploy in production or would be too risky to deploy in production. And its power, the sandbox's power, comes from the real high performance, low level dedicated network connections that we provide across the wide area. And combining that with the advanced in-network compute and storage and accelerators and GPUs and FPGAs and programmable NICs and switches. And further enables realistic experimentation by connecting your real existing edge facilities with these smart programmable core networks across the real wide area. So that's the real power in this. It's a sandbox where you can deploy really disruptive technologies, but at a production scale. Just to make it clear, we're not trying to replace your existing tools. For example, we're not going to replace Globus. You're not going to use Fabric instead of using Globus. You're not going to use Fabric instead of using your Pegasus workflow management system. But it will be a powerful sandbox to prototype these new tools, or prototype new uses of these tools, as well as to prototype brand new tools and applications that make use of this new edge core cloud paradigm. And it'll be really difficult for us to predict the innovations that all of you come up with, new tools and new uses for the system. But it'll be really interesting. We're really interested to watch. Yeah, and these new tools will likely take advantage of the edge core cloud paradigm and strategically choose where and when for different applications and different computation is made and hosted. And it'll be interesting to see all the new tricks and ideas people come up with to make this happen. So what is the impact on cyber infrastructure? So Fabric makes it possible to experiment with these advanced programmable compute and storage in the network core, but at the scale that is almost production scale, and with the facilities that you already use. So this should empower academic researchers to invent the next generation of in-network applications and tools. So how will Fabric impact cyber infrastructure is the question going forward. So the way we think about it is that the next generation of scientific computing would be unbound from any specific compute resources. Applications will run natively just across platforms and domains, including smart in-network processing and computing. We expect that current and future Fabric users like you will produce the next generation of these novel in-network applications before these capabilities are commonly available on research and education networks. Also, the Fabric enables users to produce tools that simplify the deployment of these applications throughout the edge and core and cloud. So this is a new paradigm to run things at both the edge and inside the cloud. And there's going to be a lot of tools that scientific workflows will need to deploy things in the core. And those tools haven't been invented yet. And I think that a lot of our users will invent those tools for the future. Beyond just a place to run experiments and applications, one of the philosophies of Fabric that we really pushed for, that is sort of above and beyond what some of the previous testbeds have done in this space, is that we wanted to enable full-scale prototypes that use disruptive technologies. And what this means is that we wanted to have performance that you could use that is powerful enough and fast enough for you to run production services and production applications. But we want to keep it isolated from your production services so you can be disruptive, make a lot of mistakes, break a lot of things, and everything was kind of okay. And at the same time, we wanted to make sure that like if we wanted to have you deploy things that worked a lot like production, we wanted to make sure we connected to all the real things that you already connect to. So that was the philosophy behind Fabric. And what's great about this is that many times, like these risky and or expensive ideas that you want to put in the core of the network just never see the light of day. This is especially true if the idea requires really disruptive changes to the core of the wide area network. But Fabric enables our users to prototype at scale in a secure sandbox environment while connected to the real production facilities. So we think this is a really powerful aspect of Fabric that will allow people to do some really creative things. And what's great about this too is that once you've deployed your semi-production service across Fabric and found that it works, you can measure it, and you can then have some numbers that show that validate your idea, and you'll be able to use those numbers and that validation to justify any effort or money that might be spent transitioning from the existing production environment to some of these prototypes. Something that is really hard to do in the core of the network today. Another thing that's really powerful about Fabric is that there's this problem we have with these really high performance networks, especially in the core of the network, and it's the ability to operate and take advantage of these high bandwidth wide area networks is a really sought after skill. But it's rare. It's pretty rare in academic environments. I think a lot of people on this call probably have a lot of background in doing these things, and like plenty of people that work at Internet2 or ESNet have these skills. But it's really difficult to acquire these skills from a book or a virtualized environment or just in a classroom environment. So what's really interesting about Fabric is it provides a platform for deploying custom wide area technologies connected to real end systems, including the shared programmable systems in the core, and connected to all the real platforms on the edge. So some of these platforms could be experimental platforms like Chameleon and Cloud Lab. So what you can do is use Fabric to experiment with systems that are both really high bandwidth, really wide area, really distributed, and you can deploy, you can get really real hands-on experience deploying these technologies on this hardware, on this infrastructure, and you can make all the mistakes you want, and you're not going to bring down anyone's production environment. You're just going to bring down your experimental environment. And we think that this is a really big opportunity to develop the workforce and get people experience with these wide area technologies in a place where it doesn't matter if they make that many mistakes. So that's really, really good. And another thing about learning and workforce development here is that this is really going to be true about any big shared test bed, but it's also something that we're trying to emphasize as much as possible, is that if you publish a paper, if you do run an experiment and you publish a paper and you say, here's something I found out and it's really good and awesome and everyone should do it. And if your experimental platform you used was something you built in your lab, probably out of parts you had, and maybe your grad student took it all apart and like repurposed all the pieces after they were done with the paper, and they described the test bed in their paper, but describing a really complicated test bed is probably a full paper in itself. So there's going to be things that are left out. But if you instead do your experiments on a shared test bed like Fabric, then when you publish your paper, you can say, hey, I did it on Fabric, and everyone kind of knows what that means and knows how to recreate what you did on the same test bed. In addition, because we have really good APIs and ways to package up your experiments, you should be able to package your experiment and share it with other people so they can get an account of Fabric and rerun it. And at this point, everyone will know exactly what your experiment did and why it worked, and maybe figure out why it didn't work in the future or have some better ideas. So it's just it's a better way to describe your experiments that you're publishing, is to say we did it on this well-known shared test bed that you can use as well. So that's something we're working towards. So for this particular audience, I'm going to go a little bit into the design and architecture a little bit deeper than I already did, because I think you're going to be using it in some of your next sessions. So we'll see how this goes. So here's the picture I showed before. This is the 33 sites spread across the world, where each site is a separate individual OpenStack cloud. You'll never interact with Fabric. You'll never interact with Fabric directly via the OpenStack API. You will always use the Fabric API, but just know that there are 33 separate OpenStack clouds in the system, connected with dedicated layer 1 circuits that we control. And what we're going to do, or what we can do, is allow users to deploy cloud-like resources on any of these sites and connect them together with these. We will give the users dedicated layer 2 circuits across our infrastructure, but it'll be completely outside of the internet, completely, like, all the resources that the users allocate will be dedicated to them. And of course, I've talked about connections to the public clouds, as well as connections to various high-performance computing centers and other test beds, as well as connections to potentially your campus. So this is kind of what it is at a high level. Inside of each of the clouds is a rack of pretty normal Dell machines. They're normal, but they're pretty beefy. So it's dual socket, 32 core times 2 AMD processors with 512 gigs of RAM. So there's some of the nicer Dell machines you can get these days. They're full of PCI devices that you can add to your experiment. So a lot of them we have 3 different kinds of NVIDIA GPUs. We have Xilinx FPGAs, and the Xilinx FPGAs are interesting because they have dual 100 gig per second network ports on them. And some of the work we have two different groups. One at the ESNet and one at Northeastern University is working with us to make bitcode that run on these Xilinx FPGAs that will actually run P4 programs. So you'll be able to use these Xilinx cards to run your P4 programs that you learned about today, or during this program. There's lots of storage. So there's lots of 1 terabyte NVMe drives throughout the system, many of them on every site. And each site has 250 terabytes, so a quarter petabyte of rotating storage at each site. That's 250 terabytes times 33 sites is how much rotating storage we have. And you can connect your experiments to volumes that are allocated to you on that storage. We have the 100 gig per second switch or more. Some of them are actually 400 gig per second ports on these switches that are the data plane switches that we use to connect all this together. There's some Tofino P4 switches as well. There's only 4 sites that we're paying for this, to have them. I forget which sites they're actually going to go to. They're not there yet though. And at the same time, there are a few other sites that are voluntarily they're bringing their own P4 switch to put in their site. So there will be more than 4 sites that end up with P4s, Tofino-based P4 switches. So that's good. The network cards that we have are Mellanox ConnectX 5 and ConnectX 6 cards. They all have hardware offload, so you can actually run things like DPDK inside them, or you can run OVS inside the card. So you can actually turn these Mellanox ConnectX cards into little switches where the packets come in one port, get processed in the card, and then maybe go out the same port or a different port. And the packets never leave the card itself. So you can kind of think of these as being like little switches that you can program inside of these VMs, connected via PCI pass-through. And the important here that we do, a lot of these things have hardware offload. So when you get machines here, you're going to get a virtual machine, and it's going to be allocated. It's going to be allocated regular virtual like cores and disk and RAM. Although we don't oversubscribe anything. So when we give you compute cores for your virtual machine, those are your cores. No one else gets access to them. We don't just put hundreds of VMs on the same machines just because we can. Every core is allocated to a specific VM. And all of the PCI devices are passed into the VMs via PCI pass-through. So this is sort of a hybrid mechanism that we came up with, where your accelerators and network cards are all going to be bare metal, but the VMs are going to be virtualized. And this is just, somewhere between having bare metal access to everything and virtualized access to it. It's kind of a nice hybrid where we can support as many users as possible and give bare metal access where needed. So this is what one of our sites look like. We call our fabric sites a hank. A hank is if you're into knitting or any kind of fiber arts, you might know that a hank is a unit of yarn that you can buy. So when you go buy yarn, you can get like a ball, a hank, or a skein, I think is the other one. So anyway, we call our sites hanks because all of our hanks of yarn will make our fabric, right? So what they look like inside of a hank is a stack of workers servers that are just OpenStack servers, or it's an OpenStack cluster with a stack of workers. Each one of these workers is just as full as possible with PCI devices, all the ones we've talked about so far. And we use OpenStack to create VMs on the servers and connect to the management switch and then out to the internet so that you can SSH into the node. But inside, we do a bunch of magic with PCI devices. So you get all these PCI devices, you access them from your VM via PCI pass-through. And so these PCI devices, many of them that have network cards or network ports, are connected to this data plane switch here. And you can see that a lot of them are connected to the data plane switch. And then the data plane switch is also connected out to the other fabric sites, and then also connected out to any local resources you might have in the campus or some other facilities locally. And then what we can do is you can deploy virtual machines and have some PCI devices on this hank or other hanks. And then we can use these data plane switches to patch together sets of ports. So if you have an FPGA with a 100 gig port, it can be patched into your ConnectX-6 card at 100 gigabits per second. Or you can have your ConnectX-6 card patched through the external link across the fabric dedicated layer 1 circuits to some other another VM that you have at another fabric site, and it'll just be patched straight through. Or you can have like your one of your PCI cards patched through to some local resource. Maybe it's a supercomputer or a data repository or something like that. That's how this sort of works. So you get virtual machines, PCI devices, and we can patch together the ports of your PCI devices to anywhere else in Fabric, based on how you describe your topology. So what does this look like at the highest level? So what you're going to do is deploy VMs across Fabric. They're going to have different sets of devices in them based on what you request, and they're going to be plumbed together across the Fabric infrastructure based on your topology. In this particular picture, I highlighted the P4 switch here because you can have a P4 switch somewhere in Fabric and then connect together with other machines and have your setup here for packets on behalf of your topology. Important things on this as well that you might be interested in: we can do layer 2 local bridges and wide area circuits, so we can give you Ethernet. But we also have something we call FabNet, which is a layer 3 service. We have an IPv4 version and an IPv6 version that is basically an internet that spans all the Fabric sites. So if you want to connect together your nodes across a network, but you don't really want to deal with the low-level aspects of it, you can connect to our FabNet and connect at layer 3. We have dedicated ConnectX cards. We have Fino switches coming soon, a few different types of storage, a bunch of GPUs, Xilinx cards that will be able to run P4 and have dual 100 gigabit per second network ports. And there are facility ports that allow you to connect all these things to external facilities, such as NSF cloud services and things like that. So this is what your experiment should look like. The idea from this particular workshop, it's interesting to think that you could deploy a set of P4 switches across Fabric and have them connect into the real systems that you already use, maybe Chameleon and Cloud Lab, which are programmable, or Amazon or Azure, or your institution or your collaborator's institution. And you can do this at geographic scale, and you can do it with bandwidths that are production capable. Whoop. I don't know what I just hit. Yeah, okay. So now I have a few example use cases. I still have, I think, probably want some time for questions, but I'll try to go over these a little bit fast then. Example use cases, these are people that are already using Fabric for various things. And one of the more interesting ones in my mind is this cryo-EM microscope at Rutgers. So what this is a microscope that it's at Rutgers. I don't know exactly what it does. I guess it gets really cold and makes microscopes better. But it has something they run on the front end of it. They call it a cloudlet, which is a bunch of services that allow people to access the microscope and control it and pull data off of it and like that. So currently they have it connected to just internet 2, and people can access it and do what they need to. But what we worked with them to do is this. So we have deployed was as just a proof of concept experiment for now, but they're gonna take it further and use it for something useful. But it connects to, we had 3 Fabric sites in a triangle. We ran something called FR router, which is so they can run their own routing system with their own routing protocols. And they just did it in a simple triangle, and we connected their cryo-EM microscope directly to one of these routers over a layer 2 circuit, so no internet involved. And then on the other side of this set of routers, we connected a set of nodes at Chameleon that's at TAC. And then we worked with the Open Cloud testbed at the Massachusetts Green High Performance Computing Center to do a similar thing. And now what you have is a dedicated wide area layer 3 service that you can control and program and put whatever protocols you want in it. And it connects your microscope with some experimental facilities that you have on the other side. So that's one of the experiments that this is the proof of concept, and they're expanding on it to do something more useful. This was just to show how it would work. There's a cosmology experiment, this is CMBS4, which is actually a telescope that's on the top of a mountain in Chile. And these are folks at University of Illinois and NCSA. And what they do is they pull lots of data from this telescope every night, and they look for transient, so this, things that are changing in the night sky. And what they've done is they want to have a connection that goes all the way to the microscope or the telescope. But for now, we don't have that connection. So what they were able to do is use our site in Miami at Florida International University and set up a simulated telescope that is in Miami, which is really the entry point of that data into the US. And then they were able to deploy the rest of their experiment across Fabric and just pull data from Miami temporarily while we work on extending the connections down to South America. So it's just kind of interesting. They were able to actually use Fabric to create their simulated topology that they want in the future, and they're actively doing this now. Another interesting one is NDN, or named data networking. Some of you are probably familiar with this. This is networking where it doesn't actually use IP addresses to address sites or nodes. Instead, it uses addresses to specified chunks of data, and those chunks of data get spread out through the network. And when somebody asks for data, they ask for it by a name, and they don't necessarily know where it's located. So this replaces the layer 3 IP, the layer 3 of the TCP/IP stack with something called named data networking. And what they're actually doing is deploying this at CERN, at the Fabric site at CERN, and they're pulling data off of the Atlas experiment and pushing it into this named data networking on Fabric, and then pulling it across into the United States. So the interesting thing about this is that in the past, named data networking has only been possible by tunneling across the regular internet. But now they're doing it sort of natively without the internet layer, without having to tunnel through the internet. So this is really exciting for them. Another experiment is Mike Zink at UMass Amherst has something called Flynet, and what they tried to do is identify tornadoes around Dallas, and they are basically what they have at Dallas, they have a bunch of little Doppler radars, but small ones, and then they have some drones, and they're connecting those together to collect data, and they're using Fabric and Chameleon to sort of strategically decide what to process at the edge versus in the cloud versus in the network. And so this is one of the projects they're working on, and they use Pegasus workflow to do that. And then finally, I added this slide for you guys. Jorge and his team has actually created a package of P4 educational, laboratories, and it's packaged, and it comes with every Fabric user has this in their Jupyter Hub environment predefined. And what this allows people to do is to run software P4 in the BMV2 environment across all of Fabric, and I think and run these experiments and learn about P4. And I think probably there's some goal to do the same thing for the P4 switches and the Xilinx cards moving forward. I won't tell you too much about this because I'm sure you're going to learn about it in the following talks. A little bit about our community. Like I say, we're not quite open until next month, but we actually have been open for a couple of years. So we have over 500 users. About 200 of them have used it in the last 6 weeks or so. I think these project numbers are a little bit old. It's probably quite a bit higher now, but we have 74 projects last time we looked. 108 different distinct organizations are represented. We have knit workshops. So those what we call our Fabric workshops. We do them twice a year. We call them knit workshops. We will have one next month. The last couple we've had 80 in-person attendees. We're trying to try to grow them and build a community around all of this. 6 different countries were represented. join the community. I'm sure you guys will probably end up joining it anyway, because I think you're going to learn about some of the P4 efforts that University of South Carolina has put on Fabric. But you can create an account by going to portal.fabrictestbed.net, sign up for our newsletter. If you wanted to come to our 7th workshop next month, you can try to come. If not, you can wait till the spring where we'll have the 8th one. You might also be interested in our ambassadors program we're going to develop soon, which is we're going to try to have a group of people that are in the community that work with us to learn about Fabric so they can bring it back to their campuses and institutions and help the people there make use of Fabric. Thank you, and I guess we're up for questions now. Does that seem about right? Am I about on time?
Thank you very much, Paul. And yes, we are open for questions. Paul, there are 3 questions. I believe I saw 3 already in the chat window. I will read them in order. The first one, will Fabric Core support SRv6? I think it's source routing version 6 USID services for user applications.
So, okay, that's an interesting question. So we actually do segment routing at the lowest level, but you don't actually see it. One thing to know about Fabric is we just give you layer 2 circuits and ports, and what you put on top of that is completely up to you. So I think in a way the answer is yes, because you could deploy whatever you like. We're not going to necessarily deploy a service that you then can just subscribe to. You would have to build your own topology and then deploy your own systems into it. Hope that answers the question. I'm trying to bring up the chat so I can read the questions too.
Yes, John, this was a question from John. Feel free to follow up if you feel so. The second question is, with the programmability in the core, I assume it is not possible to break the core.
We hope not. Really, the programmability. So there's a thing, like, one of the reasons we say the Fabric is not going to replace AL2S or any of these systems is because if you really just step back and see how we design this is not how you would design a production network, because we have this patch panel in the middle that is patching between these ports, but it's doing it using Cisco and NSO. So this is just so that we can provide flexibility to you, and we can create any of these topologies we want using software. But once you deploy one of these topologies and you find that it works, then we want to work with you and work with Internet 2 or ESNet or whoever to like try to get your production service in a more permanent infrastructure. So I don't think you can brick the core because we are isolating you in layer 2 circuits. So you could probably brick yourself somehow. Now, if we did a terrible job at writing our control framework, then we could probably brick stuff, and I'm sure that could happen. But I think once we give you something, you can brick yourself, but not us, I hope. Where are we?
I think the next one, what kind of file system is on the spinning storage?
It's block storage, so you have to put your own file system on it. So there, anyone you want. I hope. So we just give you block storage, yeah.
How would you compare the availability to researchers of Fabric comparing to Internet 2?
By availability, like I'm going to interpret that to mean like what is possible to do, because on Internet 2, the programmatically what you can do on Internet 2 are things like AL2S, which means you can create circuits across Internet 2 to the different endpoints in your ends. They do have some stuff where you can put some BGP points in the center so that you can run BGP in the middle of Internet 2. You definitely need to do that if you're connecting to things like AWS, but most people probably don't do that. But I think that's probably limit of what most people can do with Internet 2. I don't think they really want to open up all their protocols and let you program anything. And I think what Fabric is just a place where you can deploy whatever technologies you want, and if it breaks, it's kind of okay. I think Internet 2 is not really interested in letting people have that much access where they can maybe break stuff. I hope that they don't want that. I don't know if that answers the question or not. In terms of availability, like in terms of how many users we have, like right now it's pretty wide open. You can get whatever resources you want. I assume that in the future, we'll have more problems trying to like figure out who gets to go when. We do have some plans to have like an allocation system where you will have to apply for credits, and then you can use your credits to buy time on the system, kind of like they do on the HPC centers. Where are we now?
Will the YesNet SmartNIC tools be used on the FPGAs? Can we use other frameworks?
Yeah, so the FPGAs are just, yeah, you have the Xilinx FPGAs, they're U280s. You can plug these circuits into them using the Fabric software that to design your topology. And then the bit code that you put on the FPGA is totally up to you. We do have some concerns because it's pretty easy to put bit codes on an FPGA that will wedge an entire host machine, and there might be other experiments running on there as well. So if you want to do, like, we will allow you to put anything you want, any bit code you want on the FPGA, but the weirder the thing you're doing is, the more we're gonna like want to know what you're doing and kind of hold your hand or have you hold our hands when we're worried about trying to not mess up some of our machines. But yeah, like if you have a valid use case to put anything you want to on those FPGAs, we will work with you to make it happen. We'll just try to do it in a way that doesn't affect other experiments. Yeah.
Can you provide the same throughput wirelessly?
So I don't know how to interpret that. Like, we don't have any wireless, but one interesting thing is that so there's like the power test beds out there. So Cosmos and Powder and Aura and AirPaw, and I think that's all. There's one more. What am I trying to forgetting? It's fine. So we don't provide any sort of wireless connections to Fabric, but we are planning on connecting to all the power test beds. In which case, from the power test bed, you could do really crazy wireless experiments where you're controlling the specific powers of the radios and what type of radio frequencies and things like that. So you could do that, and then you could actually get the bandwidth from that wireless test bed into Fabric at whatever speeds we can provide. I suspect our speeds will be bigger than the wireless speeds, although there maybe technologies will change. The other thing is, if you wanted to connect this to your campus and have some device on your campus, if you put something wireless on a facility port on your campus, that's up to you to put whatever you like on there. We are more in that situation. We are something like an ISP, but we're providing you connections at layer 2, and then you also get to program the core. So yeah, so if you have something wireless on the end, we can support whatever bandwidth. So the question, Xilinx tool stack is available. Let's see if now. Make it easier for developers cross it. Yeah, we have we have like some of the licenses to do FPGA things or P4 things on FPGAs. Miriam Lesser at Northeastern also has a Xilinx FPGA like cluster at Northeastern University, and we're working with her, and we're kind of stealing a lot of the stuff she's doing because she's really good at it. And so a lot of what we kind of intend to make, the philosophy we have about Fabric and Xilinx is a little bit that if you're going to do FPGA things on Fabric, we kind of hope that you're not developing your FPGA bit code on Fabric. We hope that you developed it somewhere else and you pretty much know it's going to work. You just want to now scale it to the wide area. We'd hope that you would develop your bit codes on one of these more FPGA specific test beds, get it working, and then bring it to us for scale. I know NRP has Xilinx in Jupyter Lab. So yeah, so we should probably work with NRP to figure out what they're doing with Xilinx stuff. I think we're coming together, like all of the academic test beds and stuff, and Xilinx seems to be what people want to use, especially for the P4 stuff. The other group is the ESNet group is doing a P4 stuff as well on Xilinx. So they have a whole tool chain for that. And we're going to support both. Or we really support anything you guys want to, but we're trying to make it. Our hope is that some people will want to do P4, but don't want to care at all about FPGA. Our hope is to make it so that someone who only wants to do P4 can use the Xilinx cards without really having to learn the FPGA stuff, because that's hard. But that's our goal. Is that all the questions? I think that's all.
That's it. Well, thank you very much, Paul, and hopefully you will continue. We have a presentation by Ali next. I think probably let's do a 5-minute break, but I'm sure there will be some questions after Ali's presentation, because we will not do the hands-on on Fabric. However, Ali will present what is available on Fabric. So the next question would be, how would somebody open an account on Fabric and do what Ali will be doing next? And I think you point out already, but it would be nice to reiterate that.
Yeah, so we have, if you go to, I can just go here. I'm probably logged in, so let's just do this. If you go to portal.fabrictestbed.net, and yeah, I'm not even logged in, so that's good. So here you have to, accept the cookies, and then if you just hit this sign up button, it'll take you through a workflow, and you'll be signed up. It does work kind of like Genie and a lot of the other test beds work, where once you create an account, you have an account, but you can't access anything on the system until you're a member of a project that is authorized to use the system. If you're a professor or a research scientist of some type, you can then request to be a project lead, and then you can create your own project and add yourself, and then you have access. If you're a student or something like that, you'll need to get a professor to create an account and become a project lead and create a project and then add you, and then you'll have access. And then once you do log in, I can just show real quick. It's not that hard. You log in with your in-common identity. So mine's through University of North Carolina. And now I'm in. I've already logged in, I suppose. But once you're in, you can kind of see all the different projects that are available, and which ones you're in and which ones other people are in. There's a knowledge base where you can learn about things. If you click on getting started, it'll actually, quick start guide here will walk you through signing up and creating projects and such. So that's at learn.fabrictestbed.net. Also on this learn site is those forums. You can go to those forums here, and there's a place where you can ask questions. The general questions is pretty active. You can see people asking questions and people answering, so that's great. And then what you can do, the main thing here is you click on this Jupyter Hub, and this is one of the best ways to interact with Fabric, is you can log in with your identity. I like the bleeding edge one because I know it's actually working pretty well right now. I'm trying not to waste too much of his time, but this will actually spin up a instance of Jupyter Lab for me on our Jupyter Hub, and it's on Google's cloud. And when it opens, it'll actually have all of the Fabric tools, also all the Chameleon tools, and a bunch of example Jupyter notebooks that you can use to learn. And the examples are actually probably the best way to learn. I did not set this up on purpose, so there's probably a bunch of extraneous stuff in here that you guys don't want to see. But if I click here, there's a Start Here notebook. And the Start Here notebook is a list of a bunch of examples on how to do a bunch of different things. And you'll see down here, this is actually where his P4 labs. So if you click on the P4 labs, you can click on here, and now you just have a Jupyter notebook that uses the Fabric Python API to create P4 experiments. Right? And if you wanted to, you can come back here, and there's a whole bunch of other examples on how to do a whole bunch of other things. And so this is where you should probably get started. All right. That was maybe more than you wanted me to say, but
Hey, finally, one more, Paul.
Oh.
Thank you for that. If somebody wants to learn, I mean, what is the next workshop where somebody might want to enroll?
Well, so in September, I'm actually traveling a bunch to do this. We have a tutorial at SIGCOM. It's like the day before SIGCOM. So that's on September, I want to say like 9th, maybe 10th. After that, we're going to be at Internet 2 Tech Exchange. So if you come to Internet 2 Tech Exchange, we have a tutorial there. Look that up. You can sign up and we'll walk you through some tutorials. And then the other one that's in September is our actual knit workshop in Columbus, Ohio, at the end of September. If you go to our website, you can probably find that. So coming up in the next month, you got SIGCOM, Internet 2 Tech Exchange, and then the actual knit workshop. And don't have any on the schedule, but we like to have webinars. There's also a YouTube page that has some examples that are a little bit out of date now because we've made so much progress. But we're gonna work on getting those fixed up too. So yeah, so if you haven't signed up for our tutorials at SIGCOM, Internet 2 Tech Exchange, or knit, go ahead and do that.
Thank you. And that info, the details of these dates and places are in the website, right? What is fabric.net?
I assume so, yeah. A bunch of people on here have already done this. Right. Yeah. Yeah, we definitely are looking for people in this group to sign up and start playing.
Sounds good. Well, thank you again, Paul. We appreciate very much. And we will have a 5-minute break. We will come back at 2:15. We will have a demo. I mean, this is not a hands-on session, but what Elika Furi will be presenting, we'll share my screen. So rather than starting at 2, we will start at 2:15. What is available, the tutorials, step-by-step tutorials, how to program P4 on Fabric, that is coming next. Again, we will start this at 2:15 p.m. Eli, in preparation, do you want to share your screen? Just start getting ready.
Yeah, sure, I will.
All right, we're back. The next presentation will be hands-on labs over Fabric. These are a series of labs, about 6 labs that are available to learn P4 directly running on Fabric. The presenter will be Eli Kafuri. Eli Kafuri received the PhD degree in informatics from the University of South Carolina in 2023. He's currently an assistant professor in the Integrated Information Technology Department at USC. As a member of the Cyberinfrastructure Lab, he developed training material using virtual labs on high-speed networks, TCP congestion control, programmable switches, SDN, and cybersecurity. He is the co-author of the book High-Speed Networks, a tutorial that is being used nationally for deploying, troubleshooting, and tuning science DMC networks. His research interests previously include P4 programmable data planes, computer networks, cybersecurity, and blockchain. He previously worked as a research and teaching assistant in the computer science department at the American University of Science and Technology in Beirut. Eli, welcome, and I will let you share your screen.
Right, thank you, Dr. Jorge. So hello, everyone. In this session, I'm going to be just talking a little bit briefly on how we can use Fabric for cyber training, for education. And we're going to show some labs that we created here at USC that are related to P4. So it will help you understand how you can create an experiment that uses these switches on Fabric. So I'll skip this slide because we already talked about Fabric testbed in the previous session. But I'm just gonna be discussing a little bit how can we use Fabric for cyber training. Well, Fabric has a very nice property, which is basically it's using the real network, right? So things like physical propagation delays are provided to you. So if you are running a test, let's say from South Carolina to California, you're going to be using the actual physical delay. And as well, there's high-speed links. You have 100 gigabit per second links and even more. So with these, we believe that Fabric can be very useful for training when it comes to programmable switches, as well as high-speed networks, science DMZs. So if you want to measure why we don't have good performance in TCP, how can we tune TCP, learn everything that has to do with large data transfers and how we can optimize the network for that. So I think Fabric can be very good as well for that. Perf Sonar, how we can deploy a node that would allow us to do active measurements. So we can deploy also perf sonars over Fabric and learn about how to use perf sonar before we can use it in the actual production network. And also we can use it for measurements as well as for cybersecurity. And the interesting thing about Fabric is what Paul was showing when it comes to the Jupyter Hub. So that's the interface, basically, that you would use it to write your just like Python based, so you can write some instructions so that you can orchestrate your experiment. And you can see here on the right-hand side, this is an example of how it looks like. So we will have ways to basically add text as well as figures. And below each of them, you can have some code. So for example, here we are adding a layer 2 network. Basically, for cyber training, they will see that through these pictures. At the same time, there will be explanations. So any kind of training material, because you have these features, are going to be easily provided over Fabric. We started creating a set of labs over Fabric. We started with P4 switches using BMV2. That's the software switch. And the labs have kind of like a unified organization in which we start first with an overview. We talk about the background, about the topic, what is the topology, what is the objective of that lab. And then next, the second part and further parts will be step-by-step directions. So we'll assume that the learner has not worked before on P4, right, or any other topic that we are discussing. It's going to give you step-by-step instructions, and they're very guided. So there's screenshots to every single instruction that you execute. So far we have the following labs on P4. So first, preparing the environment and creating a slice, basically. So if you have, if you are interested in using P4 in a certain node in Fabric, how you can do so. Then understanding what are the building blocks in P4. So what is a parser, ingress, deparser, and we will be looking into that in the next hands-on session. Then how you can implement a parser, how you can do match action tables, whether you are using exact matching, LPM matching. Again, we're going to be talking about these later on, but all of them are available so that you can try them on Fabric. And as Paul was saying, they are available for the Fabric users. So all you have to do is just, if you are a user of Fabric, you go to the examples and you see the list of labs there. You click on the lab and then you will be redirected to the notebook for that lab, and that notebook will contain all the hands-on instructions. Another thing that we also did with these labs is basically have a different version of the BMV2 software switch. So by default, the version provided has logging enabled. And whenever you have logging enabled, the throughput is very low. So at most, you can get maybe like 50 megabits per second. So in these labs, we packaged two versions of BMV2, one with the logging, because when you are learning about P4, you want to see what happens inside your switch, how the packet is traversing the pipeline. But sometimes you want to test it with a little bit higher rates. So we have a version for that BMV2 with all the logging disabled. This way, if you try to do some experiment, you'll get higher rates. Here in this example here, and this is part of the labs, you can see that we have a P4 switch here at Starlight. So this whole node here, we deploy a software switch, BMV2 switch. And then we have a center in NCSA, the National Center for Supercomputing Applications, and the receiver in University of Michigan. And then we run a throughput test using iPerf3. So you can see here, we are getting around 1 gigabits per second, which can be really, I mean, it's not that high because at the end we are still using a software switch, but it can be enough for many experiments that has to do with basically high-speed networks. Another experiment, and this is going to be now part of the next series, which is containing more advanced labs on P4. For example, here we have the Q measurement lab, and I'm going to talk about that. I'm going to show a demo on that lab. But essentially, here we have an additional node, same as before, but now an additional node to act as a collector for Q occupancy statistics. And with the BMV2 switch, we get microsecond granularity. So you can see here, this is what we see in the terminal when we start running the test. And this is produced by BMV2 on a per packet basis. There are some upcoming libraries that we are planning to work on. One is related to PerfSonar. For those of you who are not familiar with PerfSonar, PerfSonar is a coordinated suite of tools that would allow you to run performance tests and troubleshoot the network, find the soft failures. For example, why is your link not performing? Is there an under-buffered switch somewhere that is causing the throughput to go down? So it's very useful for these kinds of scenarios, and it's deployed in Science DMZ networks. So our goal is to also have a lab library that would be teaching CI engineers and operators how to use PerfSonar. But instead of using the real PerfSonar nodes that are available, which, by the way, you can use to run the tests, we're going to be deploying these PerfSonar nodes on Fabric. And the nice thing about this is that we are not, for teaching, right? We are not using the production network. This is just the testbed that you can create. And using a simple script, you can decide to deploy nodes all over these places that are available in Fabric. They're going to be use cases, for example, if you have MTU mismatch, if you have an under-buffered device, and so on. So all of these are going to be explained in that library. Another one that we think would be interesting is learning more about TCP in high-speed networks. So we noticed that if you try to run an iPerf test or a throughput test, using network emulation. It's good enough, but sometimes it does not produce accurate an accurate behavior of how TCP would react in a real network. You can see here in this figure that we have the left-hand side. We are basically looking at how BBR is a congestion control algorithm. We are seeing how BBR infers the throughput, basically. So we are looking at BBR1 and 2. These are just two different versions of that algorithm. But the key idea to notice here is that on the left-hand side, this is emulation. So we are emulating 45 milliseconds of delay. And on the right-hand side, we are basically using the propagation delay of Fabric. So these two have the same link speed, the same RTT, pretty much very same scenario, but the left-hand side is on emulation, the right-hand side is over Fabric. And we can see that TCP here is more stable, so the behavior that TCP exhibits is different when we test with real networks. And for that reason, we believe that if we want to test also TCP in high-speed networks with 40 gig, 100 gig, it's better to do it on a real network, and Fabric can be very useful for that. So this is also a library we're planning to have. Other upcoming libraries, so we're gonna look more in P4, but this time also we're gonna be looking at the Tofino ASIC and hardware switches. Then we're gonna be extracting some granular measurements from P4 and plot them on the Grafana dashboard. Each one of these is gonna be a library. How we can write cybersecurity applications on P4, and finally, software-defined networking and Open vSwitch. We're going to look at the ONOS controller and OVS switch and learn how you can deploy an SDN solution over Fabric. And now I will switch to the demo, which is about Q Measurement Lab. Okay, so this is Jupyter Hub here. This is the interface. So now I'm inside the Fabric testbed. Again, what you can see here is we have text and figures to describe these hands-on labs. In this scenario, we are interested in monitoring the queue occupancy on the switch. And for that purpose, we have 4 sites. So in site 1, there will be a sender. In site 3, receiver. In the middle, there's a P4 switch deployed on a side. And we have a collector deployed on another side. And as I was saying, like the first part is kind of background information. So because we want to look at the queue occupancy, we want to clone the packets and generate reports that contain these queue occupancies. And to do that, we're going to be using the cloning operation. So here we are just describing what cloning is, how it works, and then what is the scenario. So step 1 and 2 are kind of the steps that you see in all Fabric notebooks. These are just to prepare the environment and import the Fabric library. But after that, you can start by creating a slice. We're going to call it Q measurement here. You can give it any name that you want. And then we need to define the sites. So this is what I was showing in the slides. We are deploying the switch here at Starlight and sender NCSA, collector IU, and receiver UMesh. So we will just hard code them here. Although in Fabric, there's a way where you can select the sites randomly, and you can exclude sites from the function that is selecting these sites. For the nodes, so at this point here, we're going to start by creating the nodes. We have 3 nodes, sender, receiver, and collector. So we will use 4 cores per node, 8 GB of RAM and 20 GB of disk space, and we're going to use Ubuntu. So you can see here that it's very easy. You can define these characteristics. All you have to do is just hard code them here. Next, we're going to add the network interface cards. So now you can see we have NICs here just by calling the add component and specify the NIC basic. Next, we're going to add a node for the P4 switch. So now we have a new node here. And that node here, this is going to be on site 2. You can see I allocated a little bit more here for the disk. Generally, you want to make sure like for the CPU, you have enough, for the switch, you have enough CPU and RAM just because it's going to be processing all the packets. We are adding now the interfaces to the switch, and then we start by doing the connection. So we connect site 1 to site 2, we connect site 2 to site 3, and then site 2 to site 4. So all of this, at this point, we did not create the slice yet. We are just defining how the slice would look like. Next, we will call the submit function. This is where we are committing and we want to deploy that slice that we just defined. Once we do that, you will be able to see here that you have some commands that you can use to SSH to your nodes. So if you want to go to the terminal and execute things there, you have to use these SSH commands to do so. And there are other information related to the network that will be displayed there. So remember, now we deployed Ubuntu. It's plain Ubuntu. It has nothing there, or to be precise, it has just the packages provided by default by Ubuntu. What we need to do is start by installing some packages. First, we're going to install the BMV2 P4 software switch. You can see here there's a script that is already provided to you. You don't have to deal with all the dependencies and compile BMV2. It's already compiled. You just have to install it. Then we're going to install NetTools just to be able to use ifconfig at ARP. This is not really required. You can still use the IP command, but just for simplicity, we are using that. Then we're going to install Scapy just to be able to craft packets, custom packets. Next, it's always a good idea to know which interface is which, so the name of the interfaces, and at the same time hard code IP addresses and MAC addresses just to make the lab simpler. Because later on, you will see that when you populate the rules for these P4 tables, sometimes, depending on how you implement the table, but you might need this information. So it's better to hard code things rather than just using the default values of the MAC addresses. So this step here will give us the interface names in S7, in S8 for each of these, right? The next step would be to turn these interfaces up. I'm sure most of you know already these commands, right? Like IP-link. It's very easy if you want to execute a command in these nodes in Fabric. All you have to do is just call execute and give it the command name. Then we will hard code the MAC addresses. So 1, 2, 3, 4, 5, and 6, just for simplicity. And then assign IP addresses. So for this leg of the network between site 1 and 2, it's going to be 1.0/24. So we are basically hard coding everything here. Then we have 2.0/24 from site 2 to site 3, and then 3.0/24 from site 2 to site 4. Next, we want to make sure that forwarding is enabled on the switch, because this is at the end the Linux machine, and by default forwarding is disabled for security reasons. So all you have to do is just enable this by setting the kernel flag here, IP forward to 1. Another thing that's important to do is to delete the routing entries on the switch so that we can force the packets to be routed to the software switch. Otherwise, the kernel will be doing the forwarding. So we call IP route delete, and then we give them the subnet. Next, we configure routing. So these are just static routes here. On site 1, we are adding 2.0/24 and 3.0/24. These are for the other 2 networks, and we do the same for the other ones, all by using IP route add command. Then we hard code the MAC addresses just for the sake of the ARP not to be processed by the switch, because at this point we are learning P4 and we don't want to have the programmer parse ARP packets and do all the processing in the switch. So we are making it as simple as possible. Okay, so all the stuff that we saw at this far are going to be common to the labs because you are just preparing basically the environment. But each lab would have different purpose. Here, for example, we are computing the queue occupancy and reporting it. So in this step here, we start by basically editing the P4 program. So we can see here on the left-hand side, you have the file explorer, and there's a folder called labs files. In that file, in that folder, you would have lab 1, lab 2, lab 3, depending on how many labs you have in that library. And each folder or subfolder there will contain the P4 files that comes as a starter. So these are not the completed ones. For example, there's a file called headers under lab files, lab 1. You can, just to make it easier, you can just click on it here and it will open it for you on an editor. Now I already filled this file just for this demo, but by default, you're gonna see it as empty and you'll have to follow these instructions to fill it. So what we are doing here, all of these details are gonna be discussed later in the next session, but essentially we are creating a custom header so that we can insert the queue occupancy in it. So it's a 48-bit field on a new header that we call queue_t. That's the type. So now we're going to instantiate from this header. We call it queue here, and we add it to the other headers that we have. So we are saying that our packets would have Ethernet, IPv4, ICMP, or TCP, and then queue. And later on, you can set which headers you want them to be valid or invalid. And here, this is the logic that you apply in the egress. So basically, if you want to do the mirroring and you want to do the cloning, all of this stuff you're going to write in the egress side of the program. And the basic idea here, I will not go into the details. Everything is explained. But the idea is we need to check if the packet is not a clone. We need to clone it because we are interested in getting the queue occupancy per packet basis. So it's not a clone. Let's create a clone for that packet. Now, if it is a clone, we need to set the IPv4 and TCP headers to be invalid. Why we are doing so? Because we don't want every packet to contain all the headers. We just want that to have the minimal information, just the queue occupancy, and that will be enough so that we can parse it at the collector and display it. So we'll proceed by doing that. You can see here we set the IPv4 and TCP invalid. Then we set the queue to be valid. We add the queue depth information to that header field. And finally, we truncate the payload. So we don't want the payload of the original packet. We just want the headers there. We can give here the ether type, some custom value because we are creating our custom protocol or custom header. Now that we have everything there, what we need to do is we need to test the program. So how can we do it? First, we're going to upload the BMV2 binary to the switch, but we are going to upload the high performance version of it. So without the logging enabled, just because we are doing queue occupancy measurement, and it makes more sense to have the high performance version rather than having the one that has logging enabled and has very low throughput. So next, and some of these steps are also common to all the labs. For example, what we do here, we are uploading the whole directory for that specific lab. This means that all the files that you modified here, for example, you added some information, here you added some other information, you save them, and it's going to upload everything to the switch, to the P4 switch. For getting high throughput, it's important with BMV2 to disable TCP offloading. So we disable that. There's a script to do so. And then we can install iPerf3 so that we can run the test. Now, on the switch, we will use the P4C, that's the P4 compiler, to compile the program. And then we're going to start the switch daemon. So you can see when you start the switch daemon, you have to tell it what are the interfaces and how you map them to logical ports on the switch. But because we got these interface names from previous steps, all we have to do is just tell it. So port 0 is going to be the first switch interface, port 1 is the second, and so on. Next, so now at this point, our switch is running. You allocate the interfaces as the logical ports. Next, we will need to push some rules from the control plane side. These are used for forwarding, right, or routing. So I'm saying here, I want the longest prefix match on the IP 1.0/24, and then the action would be to take output port number 0. So if we have a packet going to 1.10, for example, it's going to be sent out of port 0. Now, these rules are also in the file inside the folder related to that lab. So you can go there and inspect it. There's one of the labs that's available. It will tell you exactly how you can write these from scratch. So how you can populate the tables the way you want. Next, we will change the the buffer size on the P4 switch, as well as the link rate. So we will set it to around 120 megabits per second, and we will set the buffer size to be around 3 megabytes. And you can do them also using the control plane interface. How did we get these numbers? It's explained here. It's very straightforward. Now, we will start an IPv3 server on the receiver. We will start the collector process. So this is another thing that is interesting in Fabric. It's just so if there's some animation, you want to show something, a certain command, you can show them exactly how you do it. We are that contain the queue occupancy, and the other will be averaging the values. We get the SSH command for the collector, so terminal. What we do first is we test with 50 meg just to see how much time is being each packet is being spent in the switch without any buffering. So
Hello, everyone. I think Ali got disconnected. We are looking the way to troubleshoot this and get him back. So just hold us for 1 or 2 minutes and we'll be continuing the presentation.
Okay, thank you.
Lee, are you there? I think we lost you. Ellie? Well, I think we lost Ali. We'll check that he's gonna be back probably in the next minute or so. I apologize. We lost connectivity here in the network at USC, in the wired network. The air. Jose, Ali, can you hear me?
Yes.
I can hear.
I want to double check that you can hear me.
Yes, I can
Yeah,
hear you,
okay.
Dr. Herrera.
Yeah, Eli will be connecting soon, but I mean, well, there is a question. What is the relation between the demonstrated Fabric testbed and the NetLab virtual platform? The source code, the P4 code is the same. So Eli was showing all the steps necessary to run the experiments on Fabric, but you will see in the next session coming soon that the source code is the same. So you can move the code from the NetLab environment to Fabric. And of course, when you run on Fabric, you have to go through the steps that Eli was going through. So that is the relation. The reason why we decided to do these labs on Fabric is because we received feedback that is very easy to run on NetLab, but then when trying to port into Fabric, there is a challenge preparing the environment. The main point of Eli's presentation was to show how to prepare the environment and run the same code. So that was the idea. I don't see Elise still. So what we can do is we have a 245. The wired network is not up yet. I'm from the wireless. But what we can do is Eli was about to finish that. So what we can do is we will have the break right now. We had a break of 2:45 to 3. And then we will have the first hands-on session. This hands-on session will be over NetLab. So all of you have an account on NetLab. We will go very slowly in trying to show the source code step by step, how to program a data plane using P4. That is the idea. So Jose, you will be leading the next session. So we will start that session at 3 p.m. Eastern time. Jose, would you share your screen just to make sure that everyone join us or is ready by 3 p.m. And in case that you have trouble logging into the NetLab platform, feel free to unmute yourself or write in the chat window. Jose will help you to log in into the system.
Yeah, I have a question.
Sure.
Yeah, I would like to ask, because of my network, can I use the compiled virtual lab on my laptop?
Could you repeat, please?
You know, you provided the virtual lab, the whole lab
Yes.
virtual that I can mount on my PC. Can I use that instead of the NetLab?
As long as you download the virtual machine, yes. Did you download the virtual machine?
Mm-hmm. The 12 gig virtual machine.
The virtual machine that is at the bottom here,
Mm-hmm,
VM54 Lab,
mm-hmm.
exactly.
Yes, yes.
As long as you have that, Jose will confirm this, but yes, I believe you can run on your machine.
Okay, thank you.
Yeah, you can use VMware Workstation or Fusion, or I think it ran on VirtualBox as well. Yeah, if you have any problems, please let me know. I can help you to troubleshoot this.
Okay, thank you.
Sure.
And again, we will start this next session at 3 p.m. in about 11 minutes.
Patrick, I saw your message. I will be getting back to you in a minute. Let me check what happened with your NetLab account. Before that.
All right, we're back with the next session. Jose Gomez. Jose is a PhD student here at the University of South Carolina. He will be leading the first hands-on session where we will be writing a P4 program, compiling, testing, using the NetLab system. An earlier question before was, what is the relation between what the previous presenter, Eli, was showing and this one, specifically NetLab and Fabric. So the code, the P4 code that we will use are very similar, if not the same. The only thing that we wanted to highlight is if you want to run the experiments over Fabric, there are some steps, deploying the nodes, the BMB2 switches, etc., that you have to do in Fabric. That is automatically done in our environment, in our NetLab system. So with that, let's start our next session. Jose is a second-year PhD student here in the College of Engineering and Computing at the University of South Carolina. Jose is doing research on TCP congestion control, passive measurements using P4 and buffer sizing. Currently, Jose is working at the Cyberinfrastructure Lab developing P4 material. Before joining USC, he received his bachelor's degree in electrical engineering from the Catholic University in Paraguay. Jose, I will let you share your screen and continue from here.
Thank you very much, Dr. Crisigno. So let me share my screen and we'll get started with the hands-ons on NetLab. So let me share this.
Jose, and before that, I think there are connectivities on campus at USC because the NetLab is at USC. I wonder if it's a good plan to use the academic cloud. I don't know if you have that ready.
I have that ready. And
so why don't we try that? It's gonna take about 10 minutes, but I think it's worth because there are some people that are not able to access NetLab.
Okay, so in that case, this is a great opportunity to see what we have in the academic cloud. That means that you will still have access to NetLab, but besides that, we will use like a secondary platform that is a cloud-based system where you can run the same labs that we have here. So I think, Dr. Jorge, I don't know, what do you think if we start from there and then I will present the lab. So
yeah, let's start from zero. And again, this is our plan B. I mean, it is unfortunate that we are having some connectivities here on campus. That's the reason why you were able to access NetLab before and not now. But we have a plan B, and the plan B is using other servers that we have outside campus. And that's what we're going to be doing right now. Jose, I will let you proceed.
all right, so let's try this. If you check on the chat window, let me try to send this. I send an URL. That URL will initiate the enrollment process into the academic cloud. So we can do this together. And I will show you the steps. I will just give you like a few seconds so all of you can have access to that link. And the workflow is very straightforward. You don't need to do anything that is very rare or strange here. So let me use this link that will redirect me to the portal, the academic cloud. So let me check. I think my internet connectivity is a bit slow here. That's very unfortunate. So here I'm accessing, and what you will first see here is like the login, the login screen. And the first thing that you have to do is just put your email address and set a password. No, sorry. You click on register, and here is where you have to start. You register, put your full name, I'll put mine, and I will put my email address. I will use like a trick because I have several accounts here. You can just use your normal email address. And I will set a password. So let me see. Okay, we need a good password here. So now you will be receiving a verification key on your email. Use that verification key. In my case is this one, 6G2J37. And then you click on verify and your enrollment process is complete. Sorry, 1 second. You shouldn't have any issues. And then you just agree with the check boxes here, and then your enrollment is complete. So I see, Michael, that it says please wait. Yeah, it might take some time. Let's just wait a few more seconds, and I think it should be go through. So let me complete my enrollment. And then we have to wait a little bit. Probably it's because a lot of people is trying to do the same process at the same time. So
Yeah.
let's wait for a
The
few
other thing
seconds.
is that the same servers are on campus. It's a different system, but still on campus. And here we're experimenting some connectivity issues on campus. Dima,
Yes.
if NetLab is working for you, feel free to just use netlab.cc.sc.edu.
So let me see.
Zeke, the great American Zeke.
So Alex is saying that NetLab is working well. I'm glad to know that. So let me see. So let me refresh my browser. You're getting there.
Hey, how?
So this is what you will see after you complete the enrollment. You will see that you have to claim the free access. You will have access to this material in the academic cloud for 90 days. And in NetLab, you will have access to the material for 6 months. And we can extend that in case you need more time. We can extend that. All right, hopefully everybody can follow somehow. But what you will see when you are about to start a lab is the list of labs here. And what we are going to be covering in this lab is lab number 3, which is the P4 programming building blocks. And you just click on that, and that's how you schedule a reservation. Then the system will will be managing the reservation, and you will have access to the lab environment. Now I can see that the pod is initializing, and that will help us to start with the activity. So I don't know if you're still having issues. Are you using NetLab or the academic cloud? I will show you both how to access both platforms. They are pretty intuitive, and then we can start with the lab activity. But I just want to make sure that you are able to access the platform and follow the steps. Feel free to unmute or write down on the chat. Or if you're still having problems, please let us know. Yes, Sergio. Yeah, that's the lab that we are gonna do. Is lab number 3. From the P4 application and custom processing library. That's the one that we are gonna be using. So let me move to, yeah, if you are having that issue, which is, for example, I was having that issue when you see please wait, you just refresh your browser, you use the refresh button, and that will help you to finish the enrollment process.
Jose, and I believe that NetLab is working for some people, right? So in NetLab, I don't know which one you are planning to use, but certainly for those who NetLab is working, that's fine just to stay in NetLab.
All right. So let me move to NetLab and repeat the process. 1 second. What I will do now, this is our NetLab. I will put the URL in the chat window. So for those who can access NetLab, 1 second. I put the URL in the chat window, and what you can do next is accessing the platform with your email address and the default password, which is the one that they provided you in the email. Write down on the chat if you have a problem accessing NetLab. My colleague Ali will troubleshoot that. I will use my username and password here. Oh, sorry for that. Once you access NetLab, look, I can see that many of you were able to successfully log in into NetLab and schedule a reservation. I'm glad to see that. And for those who are using the academic cloud, it's just finishing the enrollment process and clicking on lab number 3, which is the one that we're gonna run. So what I'm gonna do now is showing you how to schedule a reservation. You go to here on the press on the blue button, select schedule a lab for myself, and then you probably have 1 or 2 courses. The course name is Workshop on P4 Programmable Switches, August 2023. That's the one that we are going to use. You can see that you have access to 2 libraries, and the library that we are going to use for this demo is the second library, which is P4 Application and Custom Processing. I will click on that, and then I will select lab number 3. You click on that, and you will see all the available pods. These are the pods. For example, this one is a pod, this is another pod. You can use any of these. If you need more pods, you just click on the right arrow, and you will see that you have many pods available here. You have a calendar application if you want to schedule reserve ahead of time. But if you want to schedule right away to do this lab, you click on the red line. So that means that you will be able to schedule the lab right away. Yes, Michael. Do you have Okay. I will click on the red line, and then you can click on the calendar icon here, and you will be able to schedule your lab for a longer period of time, in this case, 1 hour and 10 minutes. Then you click on submit, and you should be able to schedule a reservation. So I will access my reservation. You will see your pod being initialized here. And what you do next is click on Enter Lab. Once there, you will see a similar environment as you see in the Academic Cloud. So now this is Academic Cloud, and this is what you're going to see in the lab. Pretty much the same. You feel free to proceed with any of those. The steps and the machines are consistent, and all the things that I'm going to show in this demo are reproducible in both platforms. So before we start, let me go back to my slides. So I will talk a little bit about the labs and what we are going to do in this demo. So let me switch here. So as I mentioned before, you have access to 2 lab series. In the first lab, which is Intro to P4, we basically have 8 labs and 6 exercises. In this series, we navigate over the basic components of P4. We talk about Mininet, which is the network emulator that we use to run these labs. We talk about PMB2, which is the target software switch that we use to run the P4 switch. This is lab number 3. Programming building blocks is the same. We talk about the parser, match action tables, how to manage match action tables, and how to do checks on recalculation and the parser. In the more advanced series that we are going to cover now, we cover in the first 3 labs are like an introduction to P4 as well, but then we start deviating and we talk about custom headers, queue monitoring, header stacks, measuring flow sticks, and calculating inter-arrival times. These are more advanced labs, but we make sure that if you can gradually follow this, if you have some knowledge of before you already have some experience, you can easily start with this. But if you have some issues, you might want to understand what is a parser, match action table. I recommend doing the Intro to P4 series. In this lab, what we are gonna do is we are gonna talk about the components of a P4 program. For that purpose, we are gonna use the V1 model, which is the switch architecture that is implemented on top of EMB2, which is the software switch, and has the following components. It has a programmable parser, programmable match action pipelines at the ingress and egress, and a programmability parser. Each component in this architecture has a file associated. Headers.p4. In this file, we define the headers. We have the parser. We have another file for the ingress, another for the egress, checksums, and that's all the files that we are gonna be navigating in this activity. What we are gonna do as well is we are gonna see the workflow with this lab. You are gonna see how we run a topology, a simple topology like the one that you are seeing here with 2 hosts and 1 switch, and how to compile a P4 program, how to load that the compiled P4 program to the software switch, and then how to run basic tests so you can test if your P4 program is working well. We are gonna do that. And here in the remaining slides, I just want to repeat, these are the credentials that you should use. And if you have any issues with logging into the platform, please let us know. We will be happy to troubleshoot that. All right, so I will go back to where I was before. I will select NetLab, and the first thing that you should notice here in If you click on the Content tab, you will see the lab manual. This is the material that is associated to the lab. Let me just, if you go here, you click on this tab, you can undock this. And what I'm gonna do is I'm gonna put this on the side, and I will put my topology here. So here I have the lab manual. The lab manual basically provides you a comprehensive description of this activity. You will have an overview, the objectives, and the lab settings. If for some reason you need to execute any command in the virtual machines that we are going to use in this lab, the credentials are admin and the password is password. So that's all what you have to know. We have the lab roadmap. After that, we have a short explanation about the topic that is covered in this lab. We talk about the PISA architecture, which is a switch architecture. We talk about the components of the pipeline. Then we specifically talk about the V1 model, which is the one that we are going to be using in this lab, and the files associated to this. All of these are contained in the introduction. And once you are done with the introduction, you jump to section 2, where you have the step-by-step procedure. And what we are gonna do first is accessing the virtual machine. You can click on the client host, and you can see that this is a virtual machine running a light Ubuntu version that has all the necessary applications that we need to run this lab. In step number 1, we are gonna open MiniEdit.
Jose, you might want to just make sure that wait for a few seconds or a minute so everyone is on board. It seems also that the connectivity issues have been solved apparently. So probably NetLab is working very well at this point. So why don't just so everyone is on board?
Sure. I will stop here for a few seconds. All right. So is there any way to maximize the window in the VM? Yes, there is. What you can do is the following. If you go here on the tab, you can see that you have some options. Select undock, and that will take you, will open the VM into an independent screen, and then you can use the full screen there. You can do that. So let me do the following. I will dock this again because I want to show you the VM with the steps there. So here we have a password issue. My colleague Ali will be happy to help you, and he will get back to you. I will wait a few more for a moment so everybody can join me in the step-by-steps.
Yeah, there's one comment from Harish Chandra. Adi, would you please reset the password for Harish Chandra?
Yeah, I'm
You
working
can
on it.
see in the chat window. Could you repeat again?
He's troubleshooting. He's
Yes.
doing that. All right, another thing that I want to mention, this platform that we are using here, this is NetLab. This is a very useful platform to to learn to run labs, to run labs that are repeatable. However, you might wanna go further with before and you wanna do custom things. Maybe NetLab is not that appropriate for that because every time you end a reservation, the virtual machine will be restored to its initial state, meaning that all the changes that you made, any code that you wrote there, will disappear, will be deleted. So if you need the VM for any specific material or a lab that we have here in the CA lab, please feel free to contact me, and I will be sharing with you the material. So here Feng saying in the lab I have reserved a lab, but I don't know how to enter the node. That's not a problem. If you already reserve a lab, what you will see after you are done with your reservation is something like this. You will see your reservation here, and what you have to do next is click on Enter Lab. Then you will see the lab environment, which is just one virtual machine, the client machine. You click on that, and that's how you get access to the virtual machine. If you want to get access to the lab manual, you click on Content, and that's the lab manual. All right, I don't know if you have any other questions, so I can proceed with the steps here.
Yeah, I think we can proceed, Jose.
All right, so I was here starting with the lab, and the first thing that you have to do is opening mini edit, which is a graphical user interface that we use to create topologies on Mininet. The password is password, and this is the environment in Mininet. We already prepared the topologies, so no need to create the topology. You just click on File, then Open, and select lab number 3, and you will see the MN file, which is the topology corresponding to this lab. You click on Open, and that's the topology. So no need to create the topology. Then after that, on step number 3, we run the emulation. This is we are using Mininet, which is a network emulator that is using actual traffic, real traffic, and real protocol stuff. It's not like Packet Tracer, which is a simulator that uses deterministic numeric models in order to reproduce network behavior. We are using, in this case, a tool that allow us to experiment with real traffic. So on the next step, you can see that our components are grayed out, meaning that our emulation is running. And the next step is opening a terminal. I will right click on host H1 and select terminal. This is a Mininet terminal corresponding to host H1. And what I'm gonna do here is I'm gonna run a ping command. I will ping host H2. Let me put this here. So I'm here, and I will try to ping host H2. And as you can see, the test is unsuccessful, meaning that we have some issues. And the issue is that we don't have any P4 program running on this switch. We have to create the P4 program and load it to the switch, then run it in order to enable some kind of connectivity. I see a question here. John is asking, can we cut and paste between windows? Unfortunately, that's not possible with this platform. With NetLab and Academic Cloud, you won't be able to you won't be able to, for example, copy a command here like this one and paste that. So that's a limitation that we have with this platform. But as well, that limitation forces you to go over the step-by-step procedures as well. On the next step, I will use the Linux terminal. I will launch the Linux terminal in order to open the programming environment. You can just proceed by clicking on the icon here on the taskbar, or if you prefer, you just click here on the terminal located on the desktop. So let me open that. And step number 2, I will open the Visual Studio Code by issuing the following command: code before _ labs/lab3. This will open Visual Studio Code, where we have all the resources that we need in order to write a before program, compile it, and send it to the switch. So here you have the before files, the navigator. You can navigate here, and you have the coding area here. And also you have a Linux terminal on the bottom where you can execute commands. So let's dive into these components and see what we have here. Actually, in this lab, we are not gonna do any complicated things with before. We are gonna navigate over the components that we have in this pipeline. So what you can see here on the basic.before file is that we have the resources corresponding to the libraries and the headers. The first one is the core.before, which is a common library that is available for all the before 16 architectures, and you have a target specific, which is the V1 model, which has all the elements before elements that are associated to the V1 model. And then we have the files corresponding to the parser, checksum, ingress, egress, and the parser. These are user-defined libraries that we are gonna be navigating over. On step number 2, we are gonna open the headers file. The headers file, you can see if you are familiar, if you are completely new to before, but if you are somehow familiar with Java or C, you can see that we can define in before, we can define constants, we can define custom data types like this. We can define headers. Here we have an Ethernet header. Here we have an IPv4 header. I am just gonna show you this. In the next lab, my colleague Ali will go deeper into more explanation about the file, the structures, the data structures that you see here. Then what we have is the parser. We have the parser, which is basically a control block that is available in before. You can see that we include the headers. We are going to use what is inside the headers file. And you can see that this is a control block that receives a packet, which is a string of unformatted bits that we are going to parse and identify. And as a result of that, produces a header, which is a data structure that can be interpreted by the other stage of the pipeline. And basically, I'm not gonna go into details because this is covered in the other lab activity. We have several states here: a start state, a state where we extract the Ethernet information, and the IPv4 information.
Jose?
Yes.
There's one attendee that couldn't make a reservation, but there are empty slots. So can you briefly show how he can navigate through the empty slots through the arrow. Did you show that?
Sure. Sure. Let me stop here and go back. If you want to schedule a reservation, you will just have to click on the blue button here and select schedule a lab for myself. I have several courses, but in this scenario, you will see probably only 1 or 2 courses, which is the one corresponding to this workshop is this one, workshop on P4 programmable switches, August 2023. You click on that, you will see the 2 libraries that we make available for you. You click on the second one, which is P4 application and custom processing. Then you select the lab activity that we are going to run. In this case is lab 3. Once there, I can see that you can see these are the pods that are available. You can see that it's kind of reserved, but if you click on the right arrow, you will be able to see that there are many pods available. You feel free to select any of this. And if you click on the red line, you will be able to schedule a lab right away. There you will have this start time and end time selector. You can select, for example, to do a reservation for 1 hour and 18 minutes, and then you click on submit, and then you schedule a reservation. I will cancel this because I already have a reservation running, but what you will see next is something similar to this. You will see your reservation, and what you have to do is click on enter lab. Once there, you click on this icon, which is the virtual machine that we are using to run the labs, and you have access to the lab manual as well if you click on content. This is the lab manual. And as I did before, you can download the lab manual or you can undock this, but I have it already undocked on the left-hand side, so I won't do that. So I hope that answers your questions and you can join us in this activity. Is there any other questions, concerns, or comments?
I think we're good.
All right. So we check the parser, then we have the ingress. In the ingress, we basically define how we are going to manipulate the packets. These activity are covered in lab 4 and 5 respectively. We have in this pipeline, we usually define what is called match action tables, and I am gonna skip this because this is not part of this lab. Then I will jump into the egress. In the egress, you can see that we don't have anything. We have an empty egress. So we don't apply any action here. We have the checksum, which is an external component here. For example, you can see that we are defining the checksum update of an IPv4 packet, and this is how you define it. This is explained in lab number 8 in the Intro to P4 lab series. And finally, we have the deparser. In the deparser, we receive the header that we were modifying in the ingress and the egress pipelines, and we resemble the packet and we produce a stream of bit again that is called packet. And you can see here we call the packet emit method in order to resemble the Ethernet and the IPv4 packet. That's simply what we do here. Now we are done with the blocks. What we are gonna do next is I'm gonna go back to basic.p4 and I will instantiate the V1 switch by including inside that instance all the components that we were previously covering. Here I will call it V1 switch, and sorry. v1 switch will be the main component, and inside the v1 switch, I will call the parser, which is called my parser. Then I will call the checksum verification external. Then I will call the ingress, the egress, the checksum computation, and finally the deparser, which is the last component. So let me check if I don't have any typo. Parser, verification, ingress, egress. I think it looks okay. Next step is saving this file, and now we are ready to load this before program into the software switch. Before that, we have to compile the program by running the before-c command. I will call before-c, and I will pass as an argument the basic.before file that resembles all the components of the pipeline. You can see that I don't have any error, so that's good. But what you will see is that we produce an additional file which is called basic.json. This is the binary that is resulting from the compilation, and we are going to be sending this file to the P4 switch because this is the one that is understood by the P4 switch.
Yeah, one clarification. Really, this is not a binary. This is a JSON file. But if you write, if you are programming a hardware switch like Tofino, that will be a binary. For the VMB2 switch, it is just a JSON file. It would be the equivalent of a binary in a real implementation with a hardware switch.
Yeah, that's correct. Thank you for the clarification, Dr. Pacino. And yeah, in the next step, we are gonna push the JSON file to switch S1. I will execute this command, push to switch basic.json S1. If a password is required, the password is password. So on the next step, we are gonna verify that we indeed loaded the JSON file into the P4 switch. So I will go back to mini edit. You just click on mini edit, and then what I'm gonna do next is opening a terminal on the switch. Here we have terminal. You can see that this is just a Linux CLI, and you can run Linux commands, for example, ls. So you can see the files there, and you can see that our file is indeed there. So I have a question here. If I compile those code to binary file, can it be run on the Tofino switch? That's a very good question. Actually, the Tofino switch, you have to do some modifications to adapt your code that is running here on the VMB2 switch to Tofino, because the architecture that is used by Tofino is different. So you might have to do some changes to your code in order to compile it and load it to the Tofino switch. But it won't be that different. You can definitely use the codes that we have here as a reference. All right, so now we are inside the switch. And what we are gonna do next is we have to run our before program. We are not running it yet. So what I'm gonna do here, I will run the ifconfig command. So you can see the interfaces that are available on this switch. You have the management, the lookback, and take a special look on S1 ETH0. and S1 ETH1, which is the one that we are going to use for this activity. And what we are going to do on the next step is we are going to call the simple switch instance, and we are going to map these interfaces to the switch, as you can see here. We have interface S1 ETH0 and S1 ETH1, and we are going to map to port 0 and port 1, which are the ports that we use in our P4 program. So let me run this command. Simple switch. This is the instance that will implement our P4 switch. -I is the interface, 0 is the port number, and S1 ETH0 is the interface associated to that port. We have another port and interface pair, which is 1 at S1 ETH1. Then we are going to enable the logs by adding the following parameter, nanolog. This will help us to visualize what is inside the switch, what is happening inside. IPC, and we'll write this. And finally, we pass the before the JSON file, which is like the binary file, and ampersand to run this process on the background. So let me check. Yeah, I think it's correct. Let me run it, and you can see that we have now the switch running. The next step, let me clear the screen. Now we have our switch running, but we haven't populated the rules into the switch. That's what I'm gonna do on the next step. Simple switch CLI, and I will push the rules into the switch. You can see that I successfully pushed this, and now we should be ready to test our P4 program. So I can see a question here. Michael is asking on macOS with Safari, what is the magic sequence to right click on S1? And I think you just double tap, Michael. I don't know if you tried. For example, let me actually in the following step. Yeah, in the following step, or let me just go here. I think if you double tap it, Michael, and you hold it, don't release it. You just go and select the terminal, and you should be able to open a terminal in macOS. Let me know if you can do it. We have another question here. Can you explain a little bit how when the rules CMD is loaded to the program? That's a very good question. We explained that on another lab, but let me do that pretty fast. Basically, what we are doing here is we have the rules. We created this file. Sorry for this. This file is stored inside the switch. We created this for the purpose of this lab, and we are using the simple switch CLI application, which is a control plane application that will enable us to send this rule to the P4 switch, to the data plane, from the control plane to the data plane. And actually, if you go to the rules, let me go VI lab 3 rules. You can see that basically what we have is a control plane command. In this case, is table add. We call the place where we are gonna be adding those rules, which is in the ingress block, to the table called forwarding, and we are calling the action my ingress forward. And here you have the action data, which is the port number, meaning that basically, just take it simple. The rules here, what are telling the switch is, if you receive a packet on port 0, send it to port 1. and vice versa. If you receive it on port 1, send it to port 0, because what we are doing in this activity is running like a basic connectivity test. So I hope that answered your question, but if you want to know more about control plane commands, that topic is covered in Lab 7 in the Intro to P4 Lab series. So is there any other question? Says, I'm getting this error when trying to push the configuration to switch. Must specify at least one container source. There could be a problem. Actually, allow me to enter your reservation, Patrick. See, I cannot see you. Probably he's in the academic cloud. Probably what is causing that problem is that you didn't specify the target. So let me go back to this step.
You
Push to
misspelled
switch.
his name is Pratik rather than
Oh.
Patrick. Pratik.
Oh, I apologize for that. Here you go. Thank you. So let me see here. Push to switch basic.json S1. And I think you have also a compilation error. So that means that probably the file is invalid. So let me check here. You have my parser, my verified checksum, my ingress, my egress.
Jose, he fixed that. You can see in the next step, it shows that it was fixed, but probably the emulation is not started. This is a common error that you see when you are not running the emulation. So if you can go to mini edit and inspect there.
I see. The problem is that mini edit is not even running here. So what you have to do is simply, you just go here. You open the lab topology. You run the emulation, and then you should be able to push the P4 program. And that's it. If you go to the switch, you should be able to see the basic.json file. Yeah, that will solve the problem. All right, we have some questions here, but before we run out of time, I just wanna test the P4 program that we were building. Let me go back to my reservation and finish with the demo. So you can see what happens after we run the P4 program. So we push to the switch, we install the rules, and now it's time to test our program. We are gonna run the nano message client application, which is the application that will be listening to what's happening inside the switch. I'm gonna go to host H2, open a terminal here, and run an application called receive.py. This will be listening for incoming packets. I will go back to host H1, and I will be sending a packet to host H2. I will use this command, send.py 10.0.0.2, and the payload is hello world. So you can see that we produce the packet, which just consists of an Ethernet header, an IP header, and the payload, which is hello world. And if we go to host H2, sorry, you can see that the packet has been received. And finally, if we go to the switch, you can see all the stages that the packet went through in order to be processed by the P4 switch. Here you can see that the packet entered through port 0 and left the switch through port 1. You can see all the stages involved here. You can see the parser, You can see the tables that are involved here, the checksum, the deparser, and so on. This is a resource, an application that you can use to test and debug your before program. With that in mind, I will stop here. This is all what we have for lab 3, and there you have it. Unfortunately, we have some problems, but you know now what is NetLab, what is MiniNet, what are the basic components of a P4 program, how to compile it, how to push your switch, how to run the P4 program, and how to see if the P4 program is working correctly. You have the steps here on lab 3. And I don't know if you have any questions or any comments here. I can see some.
Yeah, before that, I want to make a few comments. There were some questions that certainly we jumped. We didn't cover the details. And for those who are new to P4, I would strongly recommend to go over this library, Intro to P4 Programmable Data Planes. We tried to explain with detail all the components that Jose went pretty fast and without much detail. The reason is because we just don't have time to cover all in this workshop. But we strongly recommend start from lab number 1 all the way to lab number 8. This is the first library, Intro to P4. And yeah, after that, certainly the second library would be recommended. So we're jumping ahead on the second library because we want to cover some particular topics. But again, if you're not that familiar, probably is a good idea. Strongly recommended to go through library 1 and then library 2. All right, so I didn't see any question at this point, Jose. So what we will do next, we will have a break. 5-minute break, I believe, or we still have time to have a little bit longer break. Initially, we were planning to have a 15-minute break. Ali, how much time would you need to go to complete the second hands-on session?
We can have
10 minutes?
10 minutes break. Yeah, that's fine.
Okay, let's have a 10-minute break. Meanwhile, we will be here. Jose will be helping. Jose, I see some questions. But we will start the next hands-on session at 4:10. So 4:10, we will start again the second hands-on session. Again, we will be here helping those who want to complete this lab number 1.
Sure. Yeah, I'm glad that many of you went through the labs and are able to run it. So
you might want to share, Jose, while you answer question. I think there are some.
I think John is asking now the address is in use. Are you following up with this, Ali? There was a typo. Okay, so in this case, when this happens, let me share my screen. Let me jump into your reservation, John. When that happens, there is something that you can do. So it says that the address is already in use. That means that probably you have another simple switch instance that is running. In this case, you just kill the instance by calling the pkill simple switch command. And that should resolve the issue. And let's try running again this command. Simple switch -i. And here we need a -i again. 1 is 1. Nanolog IPC basic.json. It looks good to me. And I think now your switch is running. You just need to push the rules. Let's do that together. Simple switch CLI. These are the rules corresponding to lab number 3. And that's all what you need to test end-to-end connectivity in this topology. Let me try pinging host number 2, and you should be able to reach host number 2 from host H1. And besides that, let me stop this, and you can also see the logs by running the nano message client. That one will show you what is happening when your packet is being processed. And I hope that answers your question.
I have a question.
Sure.
I have experience working with P4 using the behavioral model, and I use like namespaces to, creating a path pair and be able to ping between them. But I was wondering if you guys have worked with like virtual machines, like VirtualBox, because I experience issues at transport layer, and for some reason I'm able to like ping outside, but the TCP and UDP doesn't work. And so I was wondering if you guys have worked with VMs instead of mininet simulations for P4.
Yeah. Ellie, I don't know if you're here, but that sounds that you have to disable the TCP segmentation of loading.
Yeah.
Let me share with
This.
you the command so you can try this on your VM running your P4 switch. You just use the ETH tool. I don't remember exactly, but we have that inside the VMs. So give me a minute. I will look for those commands so you can try it in your VMs, and that should enable TCP and UDP flows to be handled by your switch. I think we can provide an answer for that.
Okay, perfect. Thank you. Because I created P4 program for like blocking specific inner IP that is encapsulated within the GTP traffic. And when I'm using SCAPI between these namespaces, it works. But then I'm using VMware ESXi or Virtual Machine Manager, and we're trying to force this VM to communicate using this simple switch or this P4 simulation, and nothing that is related to the transport layer works. So it would be nice if you guys have a solution for that.
Yeah, sure. Let me just a minute, and I will share the solution. So what you have to do is going to let me put the command there. You go to 1 second.
Okay.
Here it is. So basically this is the command that you have to run. ETH tool offload the interface name, and then the options are X, TX, SG, TSO, UFO, GSO, GRO, LRO, RX VLAN, TX VLAN, RX hash. and stuff. So that's the command that you have to run on the VM, running your VMB2 instance in order to have TCP and UDP working.
Oh, perfect.
So
So
Elise
you guys
share with you as well. Yes.
you guys recommend to for example, if you're using virtual machine manager, you start running the behavioral model, and then you use virtual Ethernet pairs to connect it to these VMs, right? And then you just gotta run that within the host, so it enables the UDP and TCP. Okay.
Correct, because you told me that you can ping, but you cannot run TCP flows iPair for anything, right?
Yeah.
Yeah, and that's probably the step that you're missing in order to have this working.
Oh, perfect.
Okay, so let's see if there's any other questions. Yeah, the VMs have no route to public net, no, because these VMs are the purpose of this VM is training. So we don't route any traffic to the internet, and also IT support doesn't allow us to do that as well. So the VMs are isolated, but I can share the VMs with you if you wanna have the VM running on your machine or on your local platform. I can share that with you. So understand. Actually, that's a good point. We for future labs we might want to include the PDFs, so inside the VMs as well. So yeah, understand. I can do that, not exactly for this lab series, but I think that's a good advice. We have to discuss it with the team here and think if we can include this. I think it shouldn't be any problem.
Also, Jose, you might want to share, maybe like after they come from the break, that on the website there's the resources table, and that already contains a link to the P4 VM and other resources as well.
All right. Sure.
The resources that we have in the website, at the very bottom, we have resources and the virtual machine with the P4 labs, what is already in NetLab, you can download and run on your computer. And then there are several other resources like Mininet, Wireshark, ContainerNet, etc. So we will be starting again in about 1 minute. This will be the last activity for today. It's going to be a hands-on section number 2, Parser implementation. The previous lab, I know that Jose discussed quite a bit of the components of a P4 program. Rather than understanding each component, the main goal of hands-on session 1 was just to get familiar with the environment. We have a source code, we compile, we download the binary or the JSON in the case of BMB2 to the switch, and then we run more than understanding each component. Hands-on session number 2 is going to be understanding this component. What is one of the main component of a P4 programmable data plane switch is the parser. That's the goal for the coming session. This session will be led by Ali. Ali is a PhD student here at the University of South Carolina. He earned his computer science bachelor degree from Lebanese University in Beirut. He also pursued his master degree in computer science at AUB, American University of Beirut. After that, he joined USC, and he's completing his PhD degree at USC, working on cybersecurity, malware analysis. Everything that he's doing is running on P4 data plane switches. Ali is working with Tofino switches. So Ali will be talking about parser implementation. Ali, welcome, and feel free to share your screen.
Thank you for the introduction. I will go ahead and share my screen. All right. So in this activity, we will be explaining the parser implementation, which is typically the first component when you program your data plane. And all the activities that we'll be discussing and doing the hands-on are in lab number 4. So I'll just give you some background. So what's a programmable parser? Typically, this is the figure here is the architecture of the programmable switch. It's high-level architecture. And the first component that you see here is the programmable parser. It allows us to parse arbitrary headers with a finite state machine. So using this parser, you can define your states and the order of the headers that you within your packets. And so once this is the first component, and later on the packet also gets processed within multiple programmable blocks, and as you see here. But our focus in this lab is on the programmable parser, how we define the headers and how we parse them and how we transition from one state to another. If you proceed with the lab series, you will see that there's a lab kind of for every component in P4. All right. So when you get the programmable switch, it's typically a white box that doesn't understand anything. So it doesn't know what's an Ethernet, what's an IP, or how to parse them. So your goal is to define these headers based on your network and based on what you need. So the programmer, as we see here in this figure, this is the headers for the IPv4. You show version, header length, and so on. We can translate that into P4 using this syntax. So we define a header with the name of the header, and then every field and how many bits it takes. Additionally, like if you're doing research on P4, you can define custom headers. So you can, let's say you want to do some INT telemetry or other applications. You have really the flexibility of defining whatever header you expect or you want. Right? So once you define the headers, now you want to define how your switch parses these headers. So let's take an example of an IPv4 packet, which the first header is the Ethernet, and then it jumps to the IPv4. So in P4, the first state is always called the start state, and it transitions unconditionally to the next state. Okay. So in our case, because we want to parse the Ethernet, so we transition unconditionally to the parse Ethernet. And this is the translation of the P4 code we'll also see in the lab. In the parse Ethernet, what we need to do is we need to extract the Ethernet header, which contains the source, destination, MAC addresses, and the Ethernet type. And based on the Ethernet type here, we want to transition either to IPv4, or let's say we have IPv6. So we can transition to multiple states based on the condition right here. And then at the end, you have also, you can decide if you want to accept the packet or reject it. When you accept the packet, the headers will move on to the next programmable control, which is the ingress control. If you reject it, then the packet will be dropped. This is the topology of the lab. We have two hosts and one programmable switch. And our goal in this lab is that we want to define MP4, the Ethernet IPv4 and IPv6 headers. And also we will implement the parser to extract these headers from the incoming packet based and transition from one state to another. And once we program our P4 program, we will verify the expected behavior, and we also will enable logging and see how the switch is basically processing the packet. So logging is a very important feature. We will see how it works. So these are the header formats for the Ethernet, IPv4, and IPv6, and we will see how we will be able to, how we will translate it to P4 language. All right. So I'm gonna go to NetLab, and here I'll scroll and make a new lab reservation.
Yeah, and there was, before you do that, Ali, there was a question before we have to shut down the previous reservation. If you finish, yeah, please shut down the previous, but it's not essential. If you just leave that, that's fine too, because the system will automatically deallocate those resources when the time expire, the time of the previous reservation expire. Ali, go ahead. So you will start, we will make another reservation, right?
Yeah, I'm gonna make a reservation for myself. All these reservations are for the attendees that like you are working on. So click on the blue new lab reservation and schedule a lab for myself. And then here you will see, you probably have like one course, which is this one, workshop on P4 programmable switches. And here I'm doing the intro to P4 programmable data planes. So click on it. And then I'm doing lab number 4, which is parser implementation. So just be careful, there are 2 libraries that are available. So if I click on it here, and let's say all these reservations are occupied, you can click on the arrow here to find an empty slot and then click on the red line. Let's say I want to do it till 5:30 and then submit. I think maximum you can do up to 3 hours, but once these 3 hours expire, you can extend it like for 30 minutes or so. Right, so this is my reservation. Enter lab. Right, so this is the content of the lab. I'm gonna go ahead and do the same as Jose was doing to split the screen into left-hand side the content, and the right-hand side is where I'm actually doing the lab. If you just click on client here. Let me increase the font a little bit. And I'll just pause for like a minute just to make sure that everyone's logged in. Let me know if you have any issue. We can help you with. All right. So every lab is self-contained. So even if you don't have any experience or knowledge about P4, here the introduction contains everything you need to complete the lab. Definitely it's good to like follow the sequence of the lab just to understand in 100%. But I'm gonna skip over a whole section 1 and jump into the hands-on directly, which starts from section 2, step 1, sorry. So the topology for this lab is also saved on the virtual machine. So all I have to do is load it. So first I will open mini edit, double click on it, and the password is password. Next, I'm gonna go ahead and load the topology of lab 4 by clicking on file, open, lab 4, and double click on that. And here you will see the topology is now loaded, and all I have to do is just run the emulation. But if you're doing any experiment or research, just feel free to like add your own custom topology. Here we have P4 switch, legacy switch, routers, controllers. It's very flexible and powerful for research. So go ahead and click run. Now, as I said, the programmable switch is a white box, so it doesn't understand anything. So let's say it encounters a packet comes in, it doesn't know what to do with it unless you specify it. So to validate that, we'll ping from H1 to H2 and see what happens. So hold the right click on host H1. I will hold it and then click terminal. And then ping host H2 with IP address 10.0.0.2. Just send 4 packets, C4. And here you will see that destination host is unreachable. Again, that's because we didn't program the switch yet. So everything will get dropped. Right? So now moving to section number 3, defining the program's header. And now essentially we'll be jumping into the programming the parser of the P4 switch. So for that, we will be using Visual Studio Code. Let's go back to the desktop and open terminal. Now I will open the files of lab number 4 using the command code P4 labs. Make sure you select the correct lab because sometimes the headers are different or the codes are different. We provide the So now in section number 3.2, if you see here, we're recoding the headers definition into the headers.p4. As you see here, there are separate files for the P4 program, but they can all be combined into one file, which is basic P4. But for like a better readability of our code and just to understand every component, that's why we separated them. So let's go ahead and start defining some type definitions and constants. And these allow us to like have a kind of a better readable code. So it's if you're familiar with C or C++, it's kind of like the same. I will be defining a type definition for the MAC address, IP address, and I will also define a constant. So under this first command here, we'll write type def bit 48 MAC address. So later on, instead of writing bit 48, I can simply write MAC address underscore T, MAC ADDR underscore T. Another one for IP4 address. And I will also define a constant, 16-bit constant called type IPv4, and has the value of hexadecimal 800, right? Now, we will see here, once we define the now what I will do is I will define the header for the Ethernet. So the Ethernet header has the destination address, source address, and the Ethernet type. Let's see how do we do it. First, you write the header keyword and then the name of your header. In our case, we name it Ethernet, but you're free to name it whatever you want. And then instead of writing bit 48, I will write the type definition that I specified above. And the field is called destination address. The second one also MAC bit 48, and this is the source address. And the last one is the ether type. It's all right. So this is the header for the Ethernet. Now next, I will be defining the header for the IPv4, and these are the field for the IPv4. I'll just copy that. So header, I will name it IPv4 underscore. Typically, when we define header, we just augment them with underscore T as in like type. So bit 4 version header length diff serve total length version. And the last two fields are the source and destination address. And instead of using bit 32, I will use the type definition IPv4. And the last one is the destination address. So now I've defined the headers for the IPv4. Doesn't really matter if you have like a typo in the name, but it does matter if you have like a typo in the number of bits, because this is gonna affect how the switch is gonna parse it. 16. Okay. Now next, the P4 also allows you to define metadata, and these are like kind of custom fields if you want that that might be helpful for your program. In our case, it's just a simple program, so there will be no metadata. So we'll just define it as an empty structure. Step number 5, just leave the IPv6 header for now and define the structure. I will call it metadata. And this is just a command, empty, so there's nothing here, right? Now, once you have your headers, now you need to combine them into a structure. And how do you define that? Also, you write struct, and I will call it headers. So my first header is the Ethernet type, and I will call it Ethernet. My second header is the IPv4, and I will call it IPv4. So that's why we kind of like augment it with T, so that we differentiate between the instance and the kind of the struct or the header. If you have like UDP, TCP, all you have to do is just define the header of TCP, UDP, DNS, ICMP, and augment them into your headers here. So that's for defining the headers. That's what we need for now, just Ethernet and IPv4. In the next section, we will see how we will program the parser so that it correctly extracts the headers from the packet. So just let me know if anyone has a question. Right. Yes. Oh, thank you. I've missed. Oh, probably had have given me a compilation error, but thanks for correcting that. I appreciate it. All right. Now moving to section number 4, parser implementation. I will click on the parser.p4 here, and let's see what it defines. So by default, once you click on parser.p4, you will see the the initialization of the parser. It has packet in, the incoming packet, which like you have an incoming packet into the switch. This is where you can access it. You have also the headers struct that we defined earlier in our headers.p4, and we call it HDR. You have also the metadata, we call it meta, and you have additional standard metadata that are specific to the architecture, but we're not going to be talking about in this lab. There are other examples, and I think next week we will talk a little bit about the standard metadata and what information they have that we can benefit from. All right. So as we mentioned, the first state in the parser is called the start state. So let's see how do we define it. So at the start state below, all you have to do is write state. It's called start, and we will unconditionally transition to the next state. So transition is the keyword that you use to transition to move to another state. And I will want to move to a state called parse Ethernet. So I haven't defined parse Ethernet yet. I will define it in the next step. So transition parse Ethernet. Now I will add the parse Ethernet state below and see how we're gonna program it. So state parse Ethernet, open curly brackets, and then packet dot x. So what I want to do in the parse Ethernet is that I want to extract the Ethernet header, and then I want to move to the IPv4 state if the ether type matches a specific value. So extract hdr.ethernet, and then transition. Now I'm transitioning based on the condition. So what's the condition? The condition is if the header.ethernet.ether type is equal to type IPv4. So what is this type IPv4? It's the constant that I've defined in the headers.p4. So if that's true, then okay, I want to move to the parse IPv4. Otherwise, if it's not true, it's good to have like a default state, and the default here is just to accept. You can have your default to reject the packet, but in this case, we just can accept it. All right. So just be careful here. How am I accessing the headers and the fields based on the definitions that are put in the headers and here. All right. So now next I'm gonna define the parse IPv4. below. So again, state force IPv4. What I'm gonna do is that I will extract the IPv4 header, and I will transition just unconditional to accept. So accept means I'm gonna move on to the next to the ingress block. All right. Okay. So once you define, what I've done so far is I defined the headers and also I've defined the states in my parser. So now my parser is complete, and all I have to do is just Control save, and we will move to the next section, which basically compiling the P4 program and validating it. So hopefully I didn't make any typo and my program compiles without any errors. Let's try and see that. So in step number 1, to compile your program, write p4c basic.p4. I have a, so it's syntax error, headers 25. Did I?
So you added the V, IPv4, but on the top it's IP4, I think.
Oh, okay.
And the one below it as well.
All right. So hopefully, okay. All right. So now once you have the program compiled, it will generate the basic.json, and this is contains the configuration of your switch with the program that you have written. So what I'm gonna do is I will push this basic.json to the switch S1 using the command push to switch basic.json and S1. So ask for a password, the password is password. All right. So now I'm gonna go back to mini edit, and I will open a terminal on switch S1 by holding the right click, terminal. And let's verify that I've loaded the program using the ls command. And as you see here, I have the basic.json. So I need that to run the switch daemon. Additionally, you can check the interfaces of the switch. So here we have two interfaces, S1 E2H0, S1 E2H1. And we'll use that to run the daemon as well. Now I'm gonna move to the command to actually run the daemon, and it's kind of like the same for all the labs. We'll show that. Write simple switch. You specify the interfaces, the logical and the physical. So I want to attach 0 to interface S1 ETH0. I want to attach another interface 1 to ETH1, and I want to enable logging, nano-log, and finally you give it the program that you have written, which is basic.json. So simple switch -i for the interface and S1 ETH0. Another one, S1 ETH1, nano-log. Basic.json. All right. So if your command here is correct, you should see these two outputs, adding interface S1 ETH0, adding interface S1 S-port 1. All right. So now once the switch is running, I need to add the table rules that will allow me to forward packets from H1 to H2 and from H2 to H1. So how am I gonna do that? I'm gonna use the simple switch CLI, and I will give it the rules that we've also provided for this lab. So simple switch CLI, I will give it lab 4 rules CMD. And here you see these are the rules that we have added. if you want to know more about the rules, you can check, like, I guess lab 5 or 6. But you can basically add know how to add the rules, how the syntax works, and so on. All right, so now let's test our P4 program and see what happens in the switch, or specifically what the parser does when an incoming packet arrives. So first, let's enable logging in the switch. And to enable logging, I'll just write nano message client. This is a Python program. So here, now it's currently waiting for packets, and once packets arrive, it will show you what the switch is doing. Now on host H2, I will open a terminal. So hold the right click on terminal, and then run the command, the Python receive.py. So here also it's sniffing on the interface H2 ETH0 for incoming packets. Now go back to host H1 and let's send a packet from host H1 to host H2. So send py 10002, just hello world, and let's see. Okay, so initially we can see that host H1 sent a packet and host H2 received the packet, right? So that means that the switch now is able to understand and forward packets. So let's go back to switch S1 and see exactly what happened in the switch. So first line here, just before I will pause, there's a question: can I customize the nano message client to print any variables and logs I want to check? I've no experience with customizing the nano message client, but I believe I'm not gonna, like, my answer is not 100% sure, but if the Python program is pretty like forward, then you might be able to print the customized variables.
You
But
can also like execute and pipe it to another shell script that you want, where you can have like a regular expression and then basically look for patterns that you're interested in. Let's say you want to look at the parser and the next 3 lines after the parser. You can do that all in shell scripting.
Yeah, there's also another answer. You can customize it, but it accepts single word. Oh, I don't. If you have experience, so just feel free to comment more. Personally, I don't use BMV2 a lot. I use the Tofino switch. They have like their own logging program there. Yeah, so, but this one is way easier than than the one in Tofino. It's more readable for sure. All right. You're welcome. Okay, so when a packet arrives here, it shows a packet in, and means a incoming packet. It arrived at port number 0. So as you remember, we attached port 0 to S1 ETH0, which is connected to H1. So that means a packet arrived from host H1. The first state in the parser is called the start state. So here I'm in the parser, and this is the first state. The parser, the start state transitions unconditionally to the Ethernet state, which extracts an Ethernet header, and then from the Ethernet header, it checked the type and it transitioned to IPv4. So once I've transitioned to IPv4, I accept the packet. So here you see parser done, which means that the packet will no longer be in the parser, and it will move to the next block, which is the control. In the control, we don't show like any programming in the control block. Well, basically, just like it briefly, it shows you what's going on in the control block, in the ingress control block. After the control, you have the deparser, and then finally you have packet out port 1. So that means that the packet exited from port 1 and H2 received it. So really logging is a very, very important tool, and especially in P4, because sometimes it's like it's not very straightforward. So you need to know what's going on inside the switch to troubleshoot your program. Right? So this is with section number 7. We verified our program. So now let's say in my P4 program, I wanna customize it more and I wanna add the parsing capability for IPv6. For now, I only have IPv4. What I'm gonna do next is I will add the headers for IPv6 and the states and transitions for IPv6. So go back to Visual Studio Code and go back to the headers file, which is here. And now what I'm gonna do is I'm gonna define another constant for IPv6. It's called type IPv6, and then 86.86.dd. Right? Now I'll define the header for the IPv6. So header IPv6. These are the fields for the IPv6 header. Just write them quickly. This is the next header, which is the hop limit, which is the TTL. Source address is 128, and the destination address is also 128. Okay, so this is the header for IPv6. Let's move on to, I will also need to add it in the header structure header. So IPv6 and call it IPv6. Now, similarly, I'll go to the parser, and now after I parse an Ethernet, there's there's a condition on the ether type if it's IPv4, and also I want to check if it's IPv6. So if type IPv6, I want to go to another state. It's called IPv6. And finally, I need to define the IPv6 state here. So state parse IPv6. What I'm gonna extract is the IPv6 header. And then I will transition to just I will just accept it. Make sure to save and then recompile your program. It's necessary to generate another basic.json file. Oops. P4C, so there are no compilation errors. I will push it again to the switch. So once I push it to the switch, let's go back to the switch daemon, and as you see here, I will exit the nano-log message. Just write Ctrl+C. And because even if you exit the nano message, the switch daemon is still running in the background. You need to kill it and then run the switch daemon again. To kill the daemon, you write pkill simple switch. And now I'm gonna run the daemon again. So I'll just use the same command. Nothing new. And then I'll also need to, because the daemon has restarted, you also need to reload the rules. So simple switch CLI, lab 4 rules. And finally, I will enable the nano message client. So go back to host H1. And now I will send an IPv6 packet. So send IPv6, the IPv6 address of host H2, BB1, hello, word. Right. Well, let's see the nano log message for the switch S1. You see an incoming packet from port 0 attached to host H1. The parser, this is the first state, which is the start. You have the Ethernet, the second one, and then from the Ethernet, because the Ether type is type IPv6, so it transitioned to the IPv6 state. And from IPv6, it's done with the parser, and then it's ready to move on to the next Explorer. So you see the difference here. You can really see what's going on, like because there's an IPv6 packet, it went to IPv6 up because it was IPv4, then it went to the IPv4. So with that ends lab number 4. If you have any question, just please feel free to write it in the chat or just unmute yourself. And thank you, everyone.
Thank you very much, Ali. I don't see any question. Okay. This is the last activity of today, the first day of this workshop. This is a 2-day workshop. We will continue in a week from today. That is the next Tuesday, August 29. On next week, what we will have is we will talk a little bit about science DMCs, specifically about buffers and congestion control. And then we'll have our guest from Google, Neil Cardwell, will be talking about updates on BBR. If you're not familiar with BBR, this is a congestion control algorithm that is increasingly popular. He will be talking about BBR version 3, I believe. The version 1 is the one that is used in by Google. And then we will have a hands-on session number 3. It's going to be how to write a P4 program to monitor buffer occupancy. And when we talk about buffers, here is routers buffers, the memory that is used by routers and switches to momentarily hold packets. And then we will have another hands-on session, and that's what is coming next week. Again, I want to thank you all, the presenters, and all of you who log in to come to today's workshop. We will be using the same URL. We will be sending again a reminding email with all the information. The labs are available, so feel free to use, and those will be available for the next 6 months. Again, we are completing just some labs, but if you are really interested in learning P4, we recommend go over the labs one by one. So thank you, everyone, and we will be meeting again in a week from today. Have a good rest of the day.
Sorry, a quick question.
Sure.
When can these recordings be available? For today's session.
Probably by tomorrow, this is going to be online. So everything
Good.
that, yes, that you should be able to check online, and it's going to be in the website.
Thank you.
You're welcome.